Okay, welcome everyone to Miami. Actually, this is Coral Gables over here. And this is our second summer school in winter workshop for aerosol science technology. And we are so happy to have colleagues and friends from all over the world. And right over here, we do have participants from Texas Tech, from Clemson, from Alabama, right? Auburn, yes. And University of Florida, and we have some more from other places. So we are so happy to have you over here. And today we will start the workshop from 4 tutorials, which cover different aspects of aerosol science technology, including the fundamentals, including the instrumentation, including the sensor, and also for nanotechnology. And then tomorrow, we are going to have the different sessions. In the afternoon, we are going to have the demo instrumentation demo where you can have a hands-on experiences. So please don't forget about that. Oh, by the way, today, after the tutorials, we are going to have the happy hour. So for people who are participating in person, please do enjoy and mix and get to know others. And also, we'd like to welcome people who participate from the online. And now let's get started. And the first speaker is Dean Pratim Biswas. He's going to give a tutorial on the fundamentals of aerosol science technology.
Thank you, CY. I guess I have to speak on here. There are noted 18, 19 people. Yeah. Panel? Yes. Okay, great. Thank you all for coming. Yeah, there's a group online. There's a group here. Online, I won't be able to see you all, but maybe if somebody is tracking, if you have a question. But here, please pause anytime. I said, you'll get the fundamentals in 40 minutes. I'm going to zoom past these things, but there's another tutorial on nanoparticle technology. So we'll cover some fundamentals therein. Many of you I know, thank you all for coming. Some of you have taken an aerosol class. So this is like a refresher then, but try to relate to it. How many have never taken an aerosol class? No one, one, good. So hopefully you'll see some things for the first time. And most of you might be experts, so bear with me. But it's always good to refresh. And Dr. Wu mentioned we will be going to the other campus. Aerosols, at University of Miami, we have the Rosenstiel School here. Atmospheric Science Department, several of our colleagues, and over in the main campus in chemical engineering, mechanical engineering. So there's a lot of activity. Try to pick that up too, those who are visiting. And those who are from here, learn about other groups that are active. And we do things at ground level. And tomorrow you'll see, I just came by, there's actually a blimp carrying some of our instruments already up above the engineering building and collecting data. So let's see, how do I use this? Okay. Good. Yeah, that's awesome. So I'll tell you what a particle or an aerosol is, why is it important, and then focus on two things, characterization. And as I said, for some, it's a refresher, but it's good. You'll also relate to it in following tutorials and also some of the hands-on stuff and aerosol transport. Things move about, but there's also aerosol dynamics, which I won't cover here, but I'll pick on that in the nanoparticle technology class where I'm in the tutorial, where my colleague will also speak about some applications. So just firstly, references. I think any aerosol scientist should carry with them the books. Smoke, Dust, and Haze is a classic. Aerosol technology is a good first read. We also have several online lecture notes, and then there are problems of many kinds in these different topics. So I thought I'll just point these out to you. I presume these slides will be made available, so you can see them later. So what is an aerosol? If you're not an aerosol scientist, and here most of you are, I don't need to say that, but if you go out on the street and ask someone, they'll say it's stuff from a spray can, but particles are everywhere. Some of them tend to be also good. We intentionally make them. There's an intent of making them for an application, but then they don't turn out to be so good, or they meet a function, but then there's a negative side. So a particle could be both, and then some are downright ugly, okay? And of course, in this short course, summer school, you will learn about health effects of particles, many times, of course, adverse health effects. It's an enabling discipline. You know, we learn basic stuff, fluid mechanics, thermodynamics, and I'll even go back down to physics, chemistry, math. But this really is a discipline in some sense of its own, because in addition to those fundamentals, we have these small particles in the flow system. An aerosol is basically a suspended particle. Then the question comes, what is a particle? A particle is a stable cluster of molecules, right? So we are dealing with sort of transformation from individual molecules. We often refer to that as a vapor or a gas. I mean, there's of course specific terminology, but particles are a stable cluster. These molecules have clustered together. And a good example is just water vapor in the atmosphere. Those are individual or could be clusters of water molecules. But then when they all come together, they form a droplet, and they can come down because, again, of gravitational forces. And then it becomes a raindrop. The raindrop could also evaporate. There's also concepts of clouds. There are a lot of folks here, faculty, who do that kind of work. But these particles could also, the same principles could be used to make useful particles. And we then use it in energy applications, in environmental technology applications, maybe to clean it up. So some are naturally occurring, some are artificially synthesized. And today we'll just talk about the basics, right? So very quickly, we could start with molecules. And there could be molecules, of course, also have a sort of a chemical signature. Like I said, water molecules, then it's water vapor. But I could, of course, in the atmosphere, I also have nitrogen molecules. I have oxygen. I could have other organic species. So you could have multiple species. And these then begin to cluster. There's, of course, a reason why they cluster. And in the second lecture that I give today, later today, I'll talk a little about clustering. And a molecule of one type could cluster with another type, right? So we'll call it a multi-component cluster. And that is, of course, a signature, a chemical signature. And then these clusters could collide and grow. Some of the molecules could then be associated directly with the cluster. So these are all physical phenomena, or what we refer to as aerosol physics. And then, of course, they move around. And they move around because they might be in this, I gave you the example of the atmosphere. There might be a certain flow. They could be in an engineered system. And if I'm intentionally making them, I might want to capture them, deposit them. Or if they're problematic, I don't want to release these into the atmosphere. So whole bunch of applications. Of course, a majority driver is an impact on the environment. And even the water cycle, it's basically an aerosol process, right? What I was trying to describe. You can have evaporation, vaporization, move up in the atmosphere, cool down, cluster, form a droplet, come back down. That basically is the water cycle. So in the environment, these play a role. It also impacts climate. You might hear some talks on that. If I happen to inhale some of these, there could be a health effect. And then, of course, you look to the right, there's something referred to as medicine. I can intentionally make a particle and inhale it, and that then becomes a drug that I'm intentionally taking in to maybe treat a disease. So it could be an adverse health effect, but I could also use it to treat diseases. And respiratory diseases are extremely common. And if I want to counter that, maybe I want to take an antidote or a medicine that way. Energy applications, materials, agriculture, and some of these are quite new. Of course, a spray system, spraying pesticides is one application extensively used, but cause all kinds of side effects or side issues. But I could also deliver nutrients for plants to grow very effectively, maybe through the leaves, right? So the leaves have openings, and we are now growing fruits, vegetables indoors. So we could also have systems like that. And then many commodity powders. So many, many different applications. But I want to just ground ourselves, dig in a little more deeper, and figure out how we initially talk about characterizing this, right? You've got some idea that it's a particle suspended in a gas, but a particle is a cluster of molecules. So it might have a physical dimension, right? We'll refer to that as the size. A very common thing associated with size is the diameter, right? We often know if it's a spherical particle or a spherical shape, I can associate a diameter. Not all particles are spherical. So I will then have to define a size. I can also use the volume of the particle as a size metric, right? Instead of the diameter, which is a linear dimension, I can use the volume. I also need to know the amount. How many of these particles do I have, right? Because I might have many of them. So that I can then refer to as a concentration. So particle diameter is a common metric. It's easy for us to associate a linear dimension. I mentioned volume. That is basically the volume of the object, in this case, the particle, right? I could also use the surface area. And there are many times we use these other metrics because depending on the application, for example, if it's a health effect and once it's deposited in my respiratory tract, it interacts with the cells in my respiratory tract, I might want to know the surface area of this particle, right? So that could be another metric. So the amount, as I said, is the concentration, and I can just count the particles. I have 10 particles, so I'll use a number concentration, right? As the word suggests or the name suggests. I could also have a mass concentration. For example, you go to a grocery store, you sometimes count the particles. You might buy tomatoes, you might buy potatoes. I want 3 potatoes. I just want to cook one meal for myself or for my partner and 2 of us. So that is a number concentration, but more often than not, they are going to weigh that. They weigh the potatoes and they associate cost with the mass or the weight of the potatoes. Mass is the right terminology, so let's use mass. So I could have a mass concentration. Because these are suspended, I use the term concentration, and it's the number per unit volume typically, right? I'm looking at a fluid metric. It's suspended in a fluid, again, typically air, and same way with mass. So it would be the mass of particles per unit volume. So the concentrations, and I've listed some units. If I'm indoor in this room, are there particles in this room? Anyone? Yes, no? Yes, you're constantly breathing it. I'm going to start breathing harder as I get excited teaching this topic, right? So I might breathe harder than you are, but there are particles, we can't probably see them because they are small. This being the linear dimension. right? The scale, and I might use a micrometer scale, which is a millionth of a meter. A meter is about that large, and you divide it into a million parts. So we can't see them, but even in this room, if it is clean, which it should be, there's good ventilation, hopefully, there are about 1,000 particles in 1 cubic centimeter. How much is a cubic centimeter? It's a little cube, imaginary cube. Each side is 1 centimeter, which is tiny. There could be as much as 1,000 particles. I go outside, I came walking from the parking lot, there might be 10,000 million particles per centimeter cube. I stick a counter at the exhaust of my automobile, a gasoline powered engine, there could be as high as 10 to the 12 particles. So extremely high concentration. And of course, these are small, so it might not be that heavy or large mass. So we might use units of microgram per centimeter cube or microgram per cubic meter and so forth. Okay, so this is a high level, very quick description. So for each size, right, I might have a certain number of particles, and not everything is going to be the same size. You can go back to your grocery store example, or you could see, if you could see the particles in this room, there will be a range of sizes. I mean, there's a range of concentration, clean room, dirty room, and so forth, or exhaust of an engine. But there's also a variation from one size to the other, and we refer to this as the size distribution. We tend to be mathematical. We ultimately have to play with equations. You know, we just don't want to be qualitative. Even I'm giving you a qualitative description, but we need to have mathematical functions. So we define something called the size distribution function. So, and the notation is little n, lowercase n, as a function of dp. I've chosen my size metric to be the diameter. It could be any of those other metrics we talked about. And in simplest terms, the size distribution function, if it's a continuous distribution, I can just say it's the derivative of this number distribution curve, right? So for each particle size, I have a certain number. And of course, if the distribution is continuous, I can take the derivative. If it is not continuous, I can take a certain interval and count the number of particles in that interval and take the ratio. So this is the definition of a size distribution function. I can same way define a size distribution function with respect to the volume as a metric. And on the right-hand side, you can see n of v, and this is just notation, is a function of the particle volume, right? If it's all spherical particles, of course, there's a relationship between the particle volume and the diameter. And if I can plug that in, and just using the definition, there is a relationship of the diameter-based size distribution function and the volume-based size distribution function, okay? So now we also start getting quantitative. I can really bring in an instrument. You will see several instruments. So I have a size range. Typically, I tend to measure in a size interval. I don't pick one size and count the particles of that size. It's also impractical. I mean, you can see that the difference from one size to the other could be as small as a molecular dimension, correct? But we look at an interval. So this is an instrument which is giving me size ranges. That's the first column, and it's little tiny, but you could see it. The concentration is the number of particles in that size interval. And I always take a certain unit volume. So I divide by that. I have to choose a volume. And 1 centimeter cube is a good metric we use. You could use meter cube. Obviously, I could choose 10 centimeter cube, then I'll have more particles. Depends on the distribution. It could be quite complex. There could be a spatial distribution, but here this is some kind of an average. So these are some numbers, and I can do a cumulative number concentration, and that's just adding up as I increase my size, upper size interval. And then I define the ratio as the size distribution function. And please track the units. It's always good to track units. Here I'm just breezing past. Otherwise, you'd spend a lot of time even talking about units and so forth. And let's ignore the last column for now. But the delta n by delta dp, it's a simple division. And I can always do that provided delta dp is not 0. And that's why I choose an interval. It's a realistic interval, which my instrument sort of dictates in some sense. And then I get these numbers and I can take the ratio, okay? So delta dp, oftentimes we want it to be small because I want that continuous distribution, but it's never 0, exactly 0, because that would say that I don't have any differential of particles in the, there's no particle size range. So there could be other nice complex discussions around that, mathematical and physical, but let's leave it at that. Delta dp is finite, so I can take the ratio and I get some numbers, right? So that's the first, second, third, fourth column. You can see delta n by delta dp, right? These are good, these are numbers. Some of you are very familiar with numbers. Oh, it's large numbers in the small size as a peak. But for us, typically humans, we like to see a graphical plot. So this is the graphical plot. And I'm plotting on the y-axis the number concentration in that size interval. So it looks like a histogram because I have size intervals, right? So I choose a size interval and I plot the number of particles in that size interval. And you can see that it's a linear scale. So the diameter is on a linear scale, and I get a graph like that. I just told you that there are a lot of particles in the small sizes, but because it's a linear scale, I need to go up to 5 micrometers. That's where I have the data and my distribution. It really gets squished up, correct, at the left end. Those are very small intervals physically, but it's in the smaller sizes on this scale. It's a scaling factor. I can take that scale, blow it up, and that's the inset that you see. And you see there's a nice pattern to the data, which I completely lost when I plot a graph with the full scale, right? So again, this may be simple. Some of you probably learned even in high school how to plot graphs, but it's very important. And then, of course, it relates to how you present your data, what is the importance of the data, and so forth. So this is one way. Any questions, please pause and ask, and I'll be happy to elucidate further. So let me take that to overcome that, right? I now, or this is another way, that was just the number concentration in that interval, but I'm interested in the size distribution function, and it's a little nebulous at this time. Why am I even defining that? I want to get a continuous form. I want to develop models. I want to have a sort of uniform way in looking at things. So let's just assume that there's some merit in defining the size distribution function. And that is now plotted on the y-axis, again, as a linear function or a linear scale for the diameter. You see that it looks a little better. I get to see there's a peak at the lower sizes. Everything else is, of course, very low compared to those high number concentrations. I look at the inset, and then there's another pattern. But the key message here is there's a lot of difference between a number concentration curve and a size distribution function curve. Okay, so one has to keep that in mind too. Let's go another step now and see, can I do something better? And now I'm just sort of showing here the x-axis as a log function. We always know when I have a large range of numbers, it's good to use a log scale. It can either squish or extend so that I can observe it. So I plot the size distribution function. And on the x-axis, I'm just plotting the diameter in the log scale. And you can see how elegantly the structure begins to show, right? So, but we have to also make physical meaning of these. I might be interested in the total number. And then, of course, we know integration, but I also want to get a quick glimpse of it. So there are many fine features to this. And some of this is written here. So this is one way that's better than what we were doing earlier, at least in terms of a visual description. But an even better way is to take the y-axis and not use the size interval, because delta dp could be very small for the small sizes because dp is in the small size range. So I divide not by delta dp, but delta log of dp. And this really brings it out. You can see there are two peaks. They come out elegantly and so forth, right? So this is in general. It's not, of course, firm. For another application, I might need another way of plotting it, but most cases for aerosol systems that we deal with, either in the atmosphere or in engineered systems, I will plot on the y-axis delta n by delta log dp as a function of log of dp. Okay, and you can see this was the same data set plotted in these ways, and you see how different they are. And of course, I can now fit in a continuous distribution. I can take this, do all kinds of mathematical stuff and things like that. And then there's a question at the bottom: what diameter should I use to define a bin size? So I might be interested in peak 1 or peak 2 or some of the smaller peaks. What is, if I want to describe that bin, there's a range of sizes. Do I take the mean size? Do I take a log average? Those are other questions. And many times they depend on the problem or the physics of the problem that I'm trying to solve. Okay, but we are just focusing on characterization, plotting, very simple stuff. And some of you might be experts, but good to have a refresher. As many of you have taken aerosol classes, but good to remember this. You'll be generating a lot of data in the lab and so forth. I can then also move towards a continuous distribution function, because many times we want to take derivatives, we want closed form expressions. So I can then use either mathematical techniques, right? Not just operate with a histogram type plot, but try to smoothen out and get a continuous form. There are mathematical expressions that will fit this data well, if that's what I want. And many times when we run instruments, use instruments, it's going to do this for you, and you'll get a nice output which looks like this. But always remember where it's coming from. It's that raw data, that table that I showed you, how we go from one form to the other. Sometimes there are issues with this. Hey, yeah, fit this. Is this the most accurate? Is this the right way to do it? So we have to be very cautious. So very important, very simple concept, but extremely important to know the relationship of the raw data to ultimately maybe a continuous distribution function. And you'll see a lot of this in the instrument demos that are done. And as a good aerosol researcher, you should, of course, know the details of even either the inversion of the data to get this, or from the measurement and so forth. Okay, very quickly, these are some very commonly used mathematical forms. So the most common distribution that we know of is a normal distribution. And really, it looks nice, looks elegant. Everything in nature tends to be sort of normal, but we really don't like it in our field. Why is that? Of course, you see the equation. N of dp on the left-hand side is the size distribution function. Capital N is the total number concentration in the suspension, right? The total number of particles per unit volume. Sigma is the spread or a distribution, could be a standard deviation of the distribution. And dp is the size of choice. So if I pick a certain value of dp, plug it in, as long as I know the mean size, dp bar, and I know sigma, and I know the total number, I can get a value for the size distribution function, right? This is problematic because of a certain shape of the distribution we typically deal with, but also from a physical perspective. Mathematically, we like to put anything and everything. Can I set dp equal to 0 in this equation? I mean, you can do anything, free country, right? Use your value, but dp equal to 0, physically, what does it mean? There's no particle, but let's say I do it. Let's just put it in because it's a mathematical expression. I put dp equal to 0, and you see that I get a certain non-zero value for the distribution function. What does that mean? So physically, something that doesn't exist has a certain concentration. I mean, that doesn't make sense. So you can see a mathematical anomaly leads to physically something which makes no sense, right? So we don't tend to like this normal distribution, and I want to mathematically constrain this, right? How do I mathematically constrain? I just use the log function. I can never have log of a zero value. There's a mathematical sort of constraint there, right? Typically, log of 0 goes to, I think, minus infinity or something like that. It's just a no-no. So I can't even define log of 0. So I put in what we call a log normal function. Now you go back to the plots that I made with log of dp and so forth. Now you can see there's also a relationship to that. And more often than not, we use a log normal functional form for the size distribution function. Does it mean everything is log normal? No, absolutely not. But it's better than the normal distribution. At least it's mathematically, physically consistent, and I can go ahead and crank equations and so forth, right? So again, simple concepts and details, of course, you pick up the knowledge as you learn more. Once I have, let's say, a log normal form for the size distribution function, I can do some simple manipulations. I can find the fraction of particles from 0 to a certain size, capital DP, right? I just choose it. Of course, if it was the mass distribution, if I chose DP to be 2.5, this would give me PM 2.5, right? PM 10, if I set capital DP to 10. This is just a number concentration ratio. And I can integrate this out and get a closed form relationship, right? Of course, there's some mathematical jugglery, but we can interpret these relationships. You also try to see what does this physically mean. For example, I can set dp, and in this case, the mean size has been represented by a geometric mean, dpg. If I set dp equal to dpg, you can see that the log term is log of 1 on the right-hand side. Log of 1 is 0. The error function of 0 is 0, right? So f of dp over n, when capital DP is equal to dpg, the geometric mean size, I have an equal number to the left, smaller than dpg and greater than dpg. So that would be a definition of a geometric mean size. So a lot of neat things by simply playing with these expressions. Okay, you also have the moment forms of the distribution. It's not only the simple numbered distribution function. I often want to play with higher order moments. So this is just a definition of the kth moment. I integrate out the size distribution function with respect to dp raised to k and integrate it out. And I go from 0 to infinity. That's a mathematical way of saying everything is covered. We do know dp can't be 0. There's nothing at 0, but it's fine. There's no number contribution at a 0 size. Same way, I'll say there's nothing infinitely large, at least in my domain of aerosols, that the number will be, again, small or 0. So this is a physically acceptable definition. I could have a diameter moment I could have a volume moment. Again, the little v on the right-hand side is the size of the particle, right? And if it is log normal, there's a relationship of the kth moment to the 0th moment as given in this relationship. So you can see that if I know the 0th moment, by the way, the 0th moment is the total number concentration. K you set to 0, you get the definition of the total number. You could then, once you know the geometric mean size and the geometric standard deviation and the 0th moment, I can find out any higher moment, right? There's a closed form relationship. So there's also a lot of mathematical jugglery we can go through. And the higher order moments, one, of course, I already discussed. If it's the PM value, the mass concentration, I might want to calculate the third moment, which will be the mass concentration with respect to dP. I might be interested in light scattering properties. I might be interested in some other physical phenomena. I might need different moments. So it's good to know the definition of these moments, right? And then I've just written them out. You can go through it. 0th moment is total number concentration, total volume, and so forth, right? And we can have different kinds of definitions and define an average size, average volume, average surface area, and things like that. Okay. Another thing to note is the number concentration looks very different from the mass. I mean, the number distribution plot looks very different from the mass distribution plot. If I'm very interested in the small sizes in the distribution, the number gives me a good idea. But if I convert that to the mass concentration, we know that the larger particles contribute the mass. So I, in fact, lose all the detail of the small sizes. Right now, mass concentration might be an important parameter, and I might not care for the number, and it's just the total mass. So then, of course, the mass concentration curve makes sense, and I will use that. Okay, and the middle graph is a surface area distribution, and that also shifts to the right. That's a general sort of thing that we keep shifting because these are higher order moments of the distribution. Okay, I'm not going to talk about non-spherical particles. That was nice. I could associate a diameter, maybe a volume. I also need to know how to characterize non-spherical particles because they're out there. And simple examples could be bacterial particles, viral particles floating around. They may not be nice and spherical, or it could be an agglomerate of other particles in the atmosphere, dust particles, and so forth. So I can define or use fractal concepts to define the shape and then do similar kinds of things that I just talked about, right? Just to throw this out, while we are not getting into detail, there are approaches to use for non-spherical particles. And oftentimes we do that. For example, the scattering properties of an agglomerated particle is going to be very different from a pure spherical particle. And these all matter when we are using instruments, right? So we have to be very cautious as to what we do. Chemical composition, I'm going to talk even less, right? That was all physical description. But particles could have different compositions. I could have a dust particle. Here, the ocean is nearby. It could be a silica-dominated particle, sand particle, or if it's coming from some other distant or from the exhaust of my car, the composition is going to be different. Or if it's a raindrop or even a cloud droplet, the composition is going to be very different. And recall, I talked about multi-component kind of particles. So this is also important because many of the phenomena that we discuss, talk about, depends also on the composition, including maybe the transport, the growth, and so forth. There are multitude of ways of characterizing it, elemental composition. So we have devices like aerosol mass spectrometers we might use to not only give us the size, but also the elemental composition. Or I might be interested in organic species, inorganic. So clubbed kind of compositions for a range of compounds. Many times the composition could be a function of size. It's not only the number changing with size, it's the composition. Very important for air quality. It depends. I'm breathing in, you're all breathing in, breathing out, right? What are we breathing in? Some of it is going to deposit and so forth. Or I am interested in a nanoparticle technology application. You'll get some very elegant applications in the last tutorial. And what is the function? I'm now intentionally want to make these and different applications. So that's my only slide on chemical characterization. Because there are sessions on bioaerosols, or at least I think instrumentation related to measuring these things, very topical. Many folks are carrying the cold virus, the flu virus. Of course, we all got over COVID and so forth. So there was a big push to characterize these particles. By the way, many of these are airborne. So again, I'm breathing it in, breathing it out. These are various sizes. Sometimes these could cause infectious diseases. Some of these diseases, hopefully we have eradicated. Or if there's a contaminated environment, I want to have a control system to remove these. Or it could be a technology that I want to sort of use to take the DNA and sort of generate new compositions of biological particles. So very important. So this is another important category of aerosols, right? Of course, they have a chemical composition, but these are biological, literally, these are living particles. So just in summary, we have to cover another topic. So I'll pause here with size distribution function. Take home message, there is something called a size distribution function. There are integral forms of this size distribution function. We use a shape. Log normal is nothing but a shape. Not everything is log normal, but many things in nature are log normal. In engineered reactors are log normal, and so forth. The chemical characterization, and then the special category of particles which are maybe viable, alive, and so forth. So there's an added dimension to deal with, even with respect to characterization, right? So those are some topics to remember. Let's talk about transport now. You tell me when I have to stop. 5 minutes. Okay, so now speed transport comes in, so we have to move fast. Anytime a particle is moving, these particles are not just sitting around here for me to come, of course, measure them, look at them, maybe, of course, with certain instruments. They're moving around. Why are they moving around? Because molecules are moving around. Molecules make up the gas. We are in an atmosphere. Of course, we also are now going to the moon, which is a vacuum kind of situation. We are sending humans to the moon. That's a different issue. And particles will move with other transport mechanism. But here they are sitting in a bed of molecules. There's something known as the kinetic theory of gases. You might have learned molecules move around as long as the temperature is not 0 Kelvin. We are in Florida. That's why we call it the summer school. The temperature is way higher than 0 Kelvin, maybe close to 300 Kelvin or even higher. So the molecules have a velocity. As they move, they collide with the particles, and that's known as Brownian motion. Then I could have a flow, like I can hear the fans blowing air into this auditorium. That is a convective flow in the atmosphere. Yesterday was very windy. So we have, if there's a particle, it's going to interact with the fluid and move with it. And then I can have external force fields. I can use an electrical field, and we design instruments based on this. We design control devices and so forth, right? I'm not going to talk of all. Another very important thing is when a particle moves in a fluid, it tends to experience a opposing force, a slowing down force. We call it a drag force, right? Sometimes you also couple it with the inertial behavior. So if I take a particle and shoot it towards the back of this room, and assuming that there's no flow, convective flow, the particle is eventually going to slow down and even come to rest. Of course, there are gravitational forces here, so the particle will tend to settle, if that's the terminology, right? So the Brownian motion, the convective motion, but anytime a particle moves, there is a drag force. So we have to account for that. And there are concepts of the mean free path that I have to deal with. So this is the average distance a molecule moves before it collides with another molecule. Now you're really getting into molecular motion. You have to look in carefully because we want to interpret how the molecule interacts with the particle, how the molecule or bed of molecules slows down the particle, the drag force. So we really have to understand molecular motion. It comes from the kinetic theory. I can calculate the speed of molecules, and from that I can calculate this average distance it moves. Again, rushing through, but you have to read this. And depending on the size that I'm dealing with, I have different regimes. So if the particle size, I compare it to the mean free path. I don't compare to the dimension of the molecule, but the dimension of the molecule has an impact on the mean free path, but it's that average distance that it moves which determines these phenomena. So if the particle is very small compared to the mean free path, we are in a free molecular regime. If it's very large, we are in the continuum regime. There is a dimensionless number known as the Knudsen number, which is the ratio of the mean free path to the radius of the particle, or 2 times mean free path by the diameter. And that dictates what regime I'm in. And depending on the regime we are in, the force expressions, the transport expressions, the drag force expressions are different, right? So one can, of course, look at this. This is just the summary of what I just said. And then there is a famous scientist. Always good to know the history of our field. Anyone know who's this character? Not folks who have taken my class. Somebody else at the back. Who's this? 1680s. So not someone around these days. So this is a British mathematician, scientist, Newton. You know, we recall Newton for so many different things, right? From a falling apple, which could be particle motion, movement of stars, to calculate. He proposed an expression for the drag force by just observation. He really didn't understand mean free path. Newton came much later, and it was actually, this gives you a summary of the history. Newton proposed an expression for that retarding force called the drag force. Stokes, and look at it, it's about 200, 300 years later, 200, 300 years later, that he actually derived it based on fluid flow equations. And then, of course, if I'm in the free molecular regime, the particle tends to slip. There are concepts of slip, boundary condition when we solve these equations are not satisfied. So we have to account for it. And if I'm in the molecular sizes, I can use the kinetic theory of gases to also determine this retarding force. So depending on the region, we have different retarding forces. But the beauty of Newton, that's why he was a visionary. You take his expression and you multiply it by a coefficient, and it meets all these different expressions. So he had a correction factor in there. He, of course, looked at large things because he was observing them. And based on that correction factor, you can get a reasonable value of the drag force using his expression. But of course, the appropriate value for the correction factor. And people have now theoretically derived expressions for the correction factor. You can now look at a settling particle, the simplest example. You can find out the time for a small particle to settle. I think I have a table. Yeah, let's pick. I'm jumping through now. If I have a 0.01 micrometer particle in contrast to a 10 micrometer particle, a small particle, if settling is the only mechanism, is going to be in the atmosphere for 48 years. Look at this. Many of you are not that age. Some of us are. So if a particle is released today, you know, when I was born, you were not even around, it's still floating around. Of course, that if nothing else is there. So very important to be careful with small particles. There's other reasons. It's of course floating around. You walk out, beautiful weather, you inhale this small particle, and it could go and cause all kinds of impacts to your health and so forth. So, and small particles come from combustion type sources. So the chemical composition, the problems associated with that could be severe. A large particle, in contrast, is still a long time, 8 hours, but 100 micrometer particle, 5 minutes. So large particles are great. You know, the baseball, a basketball, these are huge particles of great interest. This is NFL football playoff season, but these are the small particles that excite an aerosol scientist a lot more because of the simple kind of reason. Stopping distance, as I said, I can estimate an expression for the stopping distance. I'm skipping these now because Yang has told me time is nearly up. There are devices I can design based on this, right? Impactors, I think he himself, next tutorial is yours or third one. So you'll talk about some of this. I saw your notes. So I'll skip these. The PM 2.5, it's a simple inertial device that we use, very simple, based on some of the properties I just talked about, stopping distance and so forth. I use that to find out PM 2.5, PM 10, and it's actually regulated now by the US EPA. I have to report these values at certain intervals. If it's an urban area, I have to do it more frequently compared to a rural area and so forth. Okay, let's summarize. Concept of a drag force, rush through, but particles move due to diffusion. That is just bombardment by molecules. If there is a flow, they will also move around. But anytime, and then of course I can have external force fields, which I didn't even talk about. But the key thing is whenever a particle moves, there is a retarding force. And that retarding force, we call the drag force, has really so many applications, even in designing instruments. One, it happens all the time, so we have to account for it. But I can also exploit that concept to design many instruments. So with that, I'll pause. I don't know who is next. GIU. Okay, good. Thanks. Any questions? I think no time for questions. Any quick questions? Or...
Here is one.
Okay.
So there is one.
Just mute it. Yeah.
There is one from the chat.
Yeah.
How to generate these paths from the raw data when introduce the local.
Yeah, of course, that's another very important thing. These days, we just throw the data into our computers and it creates the plot, but it's very important to track it. So from an instrument, you get raw data. Now, instruments are quite advanced that they do this for you. They're built-in algorithms, and that's great because these are good instruments with good software and so forth. But it's also good to know how they come about because depends on your application. So the raw data, as I said, is that table. Maybe very quickly, I'll try to go back to that. Is, yeah, the first two columns, that comes from some device, right? It could be a microscope, it could be a aerosol instrument. So depending on the size range, and of course, instruments are designed based on certain principles. So that I will refer to as the raw data. I can then also count the particles in a certain volume of the fluid. So that is raw data. So once I have this data, you're seeing basically a spreadsheet, and everything else after that is a spreadsheet type calculation. And of course, here I'm not giving you any homework problem. You're going to listen to many different things, but in a class, you would actually play with this data, do these calculations. So as you can see, the cumulative concentration is just the addition of the different intervals. So the first one is 100, second is 200. So obviously the cumulative till that point is 300, 100 plus 200, right? And you can write simple code to do this. And the fourth column is just the ratio, right? So you would do that calculation. And then, of course, you want to use a plotting software. And these days you have a lot of plotting software. Spreadsheet programs will also create these plots for you. Okay, good. So quick answer. Done. If there are no more questions, turn over to GRU. Is it here or? Yeah, or you can ask me any questions.
Yeah. Yes. Yes, yes.
Use this mic.
Yes.
I'm going to bring the homework.
Yeah, yeah.
For the students. I mean, that way you learn more, because this.
I put an updated
Yeah.
version of the tutorial, but I did not see it here. Can you let me know?
Oh, it's in the drive or it's in
I
the,
think in the drive.
Yeah.
But where is the drive?
We also have, yeah, it's also online.
shared drive.
Yeah.
Do you want to transfer by?
No need to, yeah. You have the,
I have to click the link.
yeah, I can click it now, it's fine.
I need to pick
Yeah.
up.
Go ahead.
Andrew.
It's here. Update it, I will download it.
It's up on Friday. It's up now. I took a picture. You saw the balloon? Yes. Above engineering. Yeah. Was very high.
Hi,
Thank you.
hi, no.
Nice to meet you.
Yeah.
Let me join.
Oh, you came. Very good.
Finally, it's
From Canomac. Hi, how are you? You came from there.
Yes, yeah.
From
But,
where? In
oh.
Japan?
no, from the New York City.
Oh, New York.
Yeah.
You're based in New York.
Yes, I live in New Jersey. Yeah.
But he could tell you about.
Oh,
We'd
yes,
love to
yeah.
partner with Canomac.
Yes, yeah. Oh, please, yeah. Let me share with me the business partnership program and so.
I think maybe we can start, maybe, yeah.
Just check outside to see if any.
Sure.
So just start talking.
Okay, everyone, welcome back to the second tutorial. But before the second tutorial, we have Dr. Pakita to introduce the Rasmus campus to us. There is this atmospheric science department over here. They are doing wonderful research related to the atmospheric aerosol and the cloud and all these things. So let's welcome Dr. Pakita.
Thank you. Yeah, thanks. I'm Pakita Zaidama, and it's a pleasure to welcome you to this campus. So for this workshop that we have this afternoon session here, in part because we're very lucky to have this site that's right next to Biscayne Bay, and it's we have this beautiful social area where you'll have the social hour after this all ends. But it also recognizes the collaboration that has been started by Dr. Biswas and the Dean of the Rosenstiel School, Ronnie Avasar, to bring the engineering and the atmospheric sciences departments together in a new collaboration that we think will generate new opportunities for students and research and collaborations. So Rosenstiel School kind of occupies a unique niche in the world of aerosol research. It's in part because of our geography, that we're in this spot in the southeast of Florida where we get a unique aerosol environment. We have long-range transport of dust from northern Africa that reaches here in the summer, and we have a leading researcher, Joe Prospero, who recognized that the importance of that in many many ways. The air quality, biogeochemistry of the ocean, the Earth's radiative balance, and in part, it's also the aerosol research here is unique in that this is a marine school, and so a lot of the research has focused on interactions with the marine environment, and aerosol deposition, gases to the ocean surface are crucial to how the life cycle of organisms in the ocean. So there aren't too many schools around the U.S. that have focused on this, part of the whole aerosol life cycle. So we're kind of proud of that, and we're really looking forward to expanding on it with the collaborations that are now ongoing with the engineering department. So besides this workshop, there's also a new course that Shangyu Wu has put together that links our departments, and we also have research collaborations across here. So welcome, and really glad to see you being here.
I think it's not share screen, yeah. Let me
This one.
This one? No,
And then you duplicate.
I need the notes. Yeah.
No, no, not this one. Otherwise, this bar will be.
Oh, okay. New share, like this. Okay. Hello everyone. Hello everyone. My name is Jiayu Li, and I'm from the Air and Aerosol Sensing Group. I'm in the Mechanical and Aerospace Engineering Department at the University of Miami. So today I would like to briefly introduce my experience of working with low-cost air quality sensors, and we mainly focus on the calibration and deployment of low-cost air quality sensors. So first, I would like to remind everyone about how air pollutions are created or generated. So there are a lot of ways there are a lot of sources, for example, including industrial activity, power generation, wildfire, prescribed burn, volcano eruption, or residential cooking or heating, transportation, dust storm, and sea salt. So all these leads to the heterogeneity of spatial and temporal distribution of air pollutants. And US EPA has regulated 4 gaseous pollutants and 3 particulate pollutants to ensure the air quality is healthy. The air quality is good. So why we care about air quality? Because the relationship between air quality and health has been well established for a while. So this is within a paper published in 1993 by Dr. Douglas Dockery. So this is the landmark Harvard 6-city study, and St. Louis was one of it. So in this paper, the author has shown a positive, strong correlation between the PM 2.5 concentration and the adjusted mortality rate. And if you think about the reality behind this finding, it's kind of cruel. You possibly did nothing wrong. You are not a smoker, and you maybe exercise regularly. But if you are in a dustier city, if the air quality is not that good, then you're expecting lifetime. If you're expecting longevity is shorter than those who live in a healthier or cleaner city. So the original findings in this paper published 30 years ago has been used by EPA in 1997. And based on these results, in 1997, EPA for the first time regulated the PM 2.5 concentration. Then people start to know, okay, PM 2.5 concentration compared to other air pollutants, gaseous pollutants, they have a stronger impact to human health. On the other hand, another side note of this publication is the second author, Dr. Arden Pope, actually is a first author of another paper we may be very familiar with. In this paper, he showed that the lung cancer cardiopulmonary mortality is associated with the long-term exposure to fine particulate air pollution. So these 2 papers build the foundation of our current knowledge about how long-term exposure to particulate matter can influence our health. And as I mentioned, this has been used in the Clean Air Act in 1997 to regulate PM for the first time. So what is Clean Air Act? So Clean Air Act, there are 4 core components, and the one we are familiar most is the National Ambient Air Quality Standard, NAQS, and that's the table I'm showing here that tell us what should be the limit of the annual and daily average PM 2.5 concentration. It also has new source performance standards, state implementation plans, and national emission standards for hazardous air pollutants. So EPA has, based on the NAQS, they have set the limit. So how can we know whether the air quality in a state meet this standard or not? Is it a toxic air or it's a clean air? So that's in that way, we will need to have federal regulated federal reference method to monitor the air, to monitor the PM 2.5. And this is the PM 2.5 monitors, federal reference monitors in year 2005. And based on this figure, this map, we can see it's not evenly distributed. In some locations, we have a denser measurements, and in some locations we don't have a lot of measurement. So that's basically is how we know, okay, air quality is very important and why we need to do measurement in the US. And if we shift our sight, to the global to the globally issue. And we noticed that actually the air pollution is the health concerns related to air pollution is more severe than we thought. This is a global mortality causality based on all ages in 2019, and we can see around 6.7 million deaths associated with air pollution. Then what do we know about global PM 2.5 or air quality? So we can see a strong disparity in global PM 2.5 distribution. And this is a paper published in 2020, and this is the model output from by combining ground measurement and satellite data. And the color represent the PM concentration, and the darker color represent a higher PM concentration, and the lighter color represent a better air quality with lower mass concentration. And we can see that in Africa and Asia, where has a lot of developing countries and with higher population, we actually are seeing a worse air quality compared to other locations or countries or areas in the world. So theoretically, for locations with, if the air quality is bad, we always assume with routinely monitoring and also with a regular federal governmental effort, we are supposed to improve the air quality gradually. But is that the case? Is air quality all over the world improve gradually over years? And we find that's not true either. And this is a map showing how PM 2.5 changes from 2010 to 2016. And in these 6 years, if the location shows a reddish color, that means the PM 2.5 increased over the past 6 years. And if it shows a grayish color, that means this is bluish color, that means the air quality improved over the past 6 years. And we sadly see that for locations with a pretty bad air quality, their problems are getting worse. And this influence quite a lot of people because that's the locations. People are more, population is more, it's more concentrated around these areas. So this, as I said, this two maps combine the results from some satellite measurement, and also it's a model output. So what do we know about near ground measurement? We always care more about near ground measurement because that's closer to where we live, right? So this is another paper published in 2019, and it calculated how many PM 2.5 monitors per 1 million people. If a location with a reddish color, again, that means they have more than 1 PM 2.5 monitors per 1 million people. And if it has a bluish color, that means they have less than 1 monitors every 1 million people. And for locations where marked as gray color here, that means they don't have publicly accessible data set, or they don't have a federal reference monitors. They have access. And then the title of this paper is quite interesting. It said, no one knows which city has the highest concentration of fine particulate matter, which is sadly true because for all the locations that we think possibly is heavily polluted, we don't have this measurement. We can only guess it. Guess the PM 2.5 concentration from satellite data and also from the model output. And another quite astonishing conclusion from this paper is, so they pair population with their nearest monitoring sites. And the average distance to a monitoring site globally is around 220 kilometers. So how can you trust a monitor that's so far away from you? So that's a major concern here. And we can see the spatial coverage and also the spatial resolution of PM 2.5 monitors are still a long way to improve. So we have introduced, okay, both in US and also globally, how the PM 2.5 monitors is and how people have identified the impact of PM 2.5. Then I would like to introduce how do we measure and understand air quality. So mainly there are three parts. So one part is the ground measurements, including traditional monitors, like the one we collect with sample filters, and the low-cost sensors, and also with the atmospheric observations. And we also have air and space observations. That means for example, the aerosol optical depth we collected from satellites, from aircrafts, balloons, and also from drones. So all of these together can be feed to the models and global models, regional models, so that we can predict the PM 2.5 concentration at locations. We don't have an estimate. We don't have a measurement. When we compare all the strongness, the strengths and weakness of all these data sources, we can find for regulatory monitors, they are expensive but provide the most accurate data, and they are the backbone of the whole system. And local sensors, they are very cheap and requires minimal siting requirement, and they can significantly improve the spatial and temporal resolution. And for the satellite retrievals, they can cover the Earth quite well. They have a very good regional coverage, but the issue is the temporal resolution is not that good. And also for example, when you have a heavy clouds or when there's a rain or snow events, this is something you cannot get your data. The simulation model, which we show here, it can provide a very good global coverage, and especially it can be used for forecasting, but it has a very limited resolution. Right now about models, I think a lot of effort has been used to build urban level models. And the reason for this is we have a lot of cities that's with a sensor deployment campaign, but we don't have the appropriate model to bridge the local model and the regional or global model as a city level, urban level model. So that's about a simulation model. So these are the most popular, or what I think is pretty popular low-cost sensors we have seen. So this is the sensor used mainly by the Carnegie Mellon University, and this is APT from Aerosol and Air Quality Research Lab, and this is Purple Air. And Purple Air right now is the most widely used sensor, and due to its price, it's around $200 to $500 to set up a node, and this is the clarity node. So what has been improved after we include low-cost sensors? This is a figure I really like. This is from Carl's paper in 2020. And so this figure is a little bit complicated. So the y-axis is the PM 2.5 annual average concentration, and the x-axis is the PM 2.5 monitors per million people. And the size of the dot at the beginning of this arrow represent the population. And we can give an example with Central Asia as an example. If we only consider regulatory monitors, there is only approximately 0.1 monitors per 1 million people. But if we consider local sensors, we can reach approximately around one monitor per million people. That's an order of magnitude improvement. So that's the reason that low-cost air quality sensors have been so popular recently. So, okay, I'm on time. So next thing I want to introduce what is the working principle of low-cost sensors. So the first one is this is a work from long ago, like 8 years ago when I was still a PhD student. So at that time, this type of sensor is very popular. We call it nephelometer type sensors. And this is from sharp sensor. So particles passing through the measuring point as a cloud, and there is a light source that casts a light on it. And the scattered light will be collected by a phototransistor and transferred to an electrical signal. And in this work, we did a me theory optical inversion, and we showed that the response of the sensor should depend on material. So what is the composition of your particle, and also the size. It varies with the size of the particle too. So what does this mean? What challenges this causes? You possibly calibrate your sensors as guided with Arizona dust in your lab, but later when you put it outside, you can see a bias caused because the size distribution or the composition has changed. And this is also another reason we see a disability of sensors performance in field. The reason is there is a seasonal trend of PM composition and also PM size distribution, and all this will lead to add some disturbance to your sensor's performance. The other one is the OPC type sensors. This is a work from Dr. Carrie Kelly's group, and this is another photo I think they just published it, and I think it's very interesting. So for this type of sensor that your particles passing through the measuring point one by one, and each time when they pass the measuring point, they are supposed to generate a pulse. Smaller particles generate a small pulse, and the large particles generate a higher pulses. And that's what we think that its working principle is. I will add some recent concerns related to this type of particles later. But this is the working principle of plant tower sensor, which is the main component in the purple air sensor. So how do we calibrate sensors? I have only one slide to introduce it. So we usually, for example, if you calibrate your sensors in lab, you need to build a chamber, and then you need to deliver your aerosols to the chamber. You put your sensors inside and and you also incorporate the reference instruments. We have used SatPac, GRIM, SMPS, and also an SMPS. So you can compare your sensor response to your reference instrument. And if you are if you are doing a field campaign to calibrate your sensors, then you can put it next to the high volume air sampler, so you can compare with the filter results, which is considered to be more reliable as a federal reference method. So this is how we calibrate our sensors. And then I want to talk about the calibration models. So calibration model is the most important part of low-cost air quality sensors. And what's the nature of it is, okay, we have sensor response. It can be digital, which means it's a unitless number. Maybe it's from 1 to 1024. It can be an analog output, and you need to definitely convert this analog output to digital too with the analog digital converter, right? And that can be from 0.5 volt, or it can be a voltage or a current. And sometimes you get a sensor, and for these sensors, so they have been pre-calibrated. So what you read from the sensor directly is already the PM concentration, such as mass concentration or number concentration. And your calibration model is the tool that you bridge from sensor response to PM concentration. As Dr. Breeze was mentioned before, it can be the mass concentration of PM 2.5, PM1, or PM10, or sometimes it can be a number concentration, which is number per cc. If we think it in another way, so this is physically how your calibration model is bridging from sensor response to PM concentration. And if we think it one step further, it is during your calibration experiments, no matter whether it's indoor or it's outdoor, you are collecting data of a certain period of time. And that's the period of time that you know the concentration range. Your calibration model is bridging it from a limited test data set to unlimited deployed data set. It can be deployed outside for a really long time. It can be deployed for 3 years, 4 years. The concentration maybe exceed 5 times of what you used during your calibration. But your calibration model enable you to have an estimation to unforeseen scenarios of your in your sensor deployment. So that's about your calibration model. We have seen so many models in the past 3 years. A lot of effort has been poured to make these sensors work better. And I did a very brief summary based on my own understanding. So one is the conventional calibration. It includes only one variable, which is your sensor output. And the one most commonly accepted is the linear model that y equals a plus x plus b. And later we see people use polynomial equations like y, like I show here. Then we see some conventional calibration methods that include multi-variables. For example, when you calibrate your PM 2.5 sensor, we have seen people include relative humidity and temperature, and you can put them to a linear relationship. You can combine all of them together. We have also seen, I don't know how, so many different things that they develop a function for each variable and then couple them together. So this is another way of doing it. So all these are conventional methods. We also have seen advanced models, including random forest, nearest neighbor, neural network. All these machine learning models, you provide your input and then you have a kind of a gray box and then you have your output model. The issue of this advanced machine learning model is the interpretability and also like overfitting and autocorrelate. And also remember your sensor time, it's a time series. So it has auto-temporal correlation, autocorrelation temporally. So you need to very carefully divide your training and test data. So what hasn't been discussed a lot, but we are very interested in my group is the categorical. Is the categorical model. So what is a categorical model? So it's discrete output. For example, you divide your PM concentration in 5 levels. 0 to 10, 0 to 10 micrometer, 10 to 12, 20, 20 to 30, 30 to 40, 40 to 50. And each time when you have a sensor output, you don't know the exact concentration, but you know, okay, it falls within maybe the 20 to 30 micrograms per meters cube level. So this will be very helpful when you have a very dynamic environment and your sensor response is influenced by a lot of factors. It can be helpful. So that's a lot of models. And this is an example. So the x-axis is the reference PM 2.5 concentration and y-axis is the reported local sensor PM 2.5 concentration. When we color all the data points with the relative humidity level, we see that the sensor's response deviates gradually from the 1-to-1 line after with a high relative humidity. So based on this, they have a hygroscopic model to correct such a bias. We see that although the R value or R square value did not improve a lot, but the bias and MAE, mean absolute error, has been decreased. So that shows how we can use humidity to correct the sensor's response. And this is part of this conventional and advanced multivariable models. So you have a model, you need to evaluate how good your model is. These are 3 metrics that I have seen most among the sensor calibration paper. So one is Pearson's R, and we are so familiar with it. It's usually between 0 to 1. The higher the R value, the better the correlation. And the next one is the root mean square deviation, RMSE, and the mean absolute error, MAE. I have listed here. It's kind of similar, just with a slightly different error distribution. So we find that one thing has not been discussed a lot is the sensor or the raw data distribution. So do you need a normal distribution, the inverse, the bell shape, when you do the linear correlation? Do you need that? No, you don't need that. So linear correlation doesn't, or single variable regression doesn't require a normal distribution, but Pearsons are actually, it requires your data to be normal distribution. But is sensor data normally distributed? The answer is no. So this is one of our work that we see how we calibrate methane sensors, and we want to see how methane sensors what's its performance outside. And actually, when you put your sensor outside, it's supposed to be a near log normal distribution. And the reason is you have so many data points in the near background level, which means there is no emission events, and you only have maybe 1% or 2% of your data exceed that range. And most of data in this range causes an issue, because this is where your sensor is very noisy, and its challenge its limit of detection. And if you include such a large amount of data in a low concentration range, it will bias your model. It will bias your regression. So what we have done is we have, for example, we sample the data, we try to convert it back to a normal distribution, and you can also use average value in each period, in each range, so that you can improve your distribution. So these are the challenges and the parameter metrics we use to evaluate conventional regressions. For machine learning algorithms, we have a different way of evaluate them. And I present two ways, which are the two most common ways here. One is called k-fold cross-validation. For example, if you have 6 data, you divide it into 3 groups. Each time you leave one for training, for test, and the other two groups combined for training. And you have a training score, test score, and you do iteration 2, iteration 3, and then you average the score from 3 different iterations. So that's the k-fold cross-validation. So the second one is called leave one out cross-validation. So what does this mean is it's an extreme value that your k equals n, which is the number of your sample. Again, we are still having 6 samples. We are still having these 6 data points. Each time we leave one out for test and the other 5 to train our model, and we rotate, and we have 6 training test scores. We average them, and then we have a overall performance of our model. So why the training for machine learning algorithms and the conventional models are different? I think one important reason is the nature of and stability of the advanced model. So if you use the same data, for example, to develop a random forest model, highly likely this time and next time is different. So we want to see how stable are these algorithms. So these are evaluation. So these 2 methods, k-fold cross-validation and leave one out cross-validation, are the evaluation metrics for machine learning algorithms. How do we use our sensors? So I want to introduce, this is our newest, most recent work about Pittsburgh Monte Carlo simulation. So we have a sensor network in Pittsburgh. We collect, that's run by Carnegie Mellon University. We collect this data set, and we also include Purple Air data set. And then we try to assign, for example, have 1,000 individuals. We imagine that we generate them, and then we assign their daily activities, like when they leave home, when they arrive home, when they go sleep. We try to assign each one individual with a specific activity pattern. Then we use Monte Carlo simulation to add some randomness to all these daily activity patterns. And then we integrate this with our sensor measurement to see how exposure of each group of people. So in another word, can your exposure level be represented by outside monitors? We know we spend 90% of our time outdoor, but most of the epidemiological studies use outdoor measurements rather than indoor measurements, right? So first thing we did is we try to see what's the difference between RAMPS data. This is the Carnegie Mellon data set and the Purple Air data set. So we see that in the raw data set, they all show a low indoor concentration and slightly elevated outdoor concentration here. We tested 4 different models, and these are 4 different models we found from literature to see their impacts to the raw data. So one thing worth noting is both the hygroscopic model and the 2-piece model is from the Carnegie Mellon University, and this EPA is from the overall so many different monitors, so many different local sensors. They have developed a general model, and this is a FIRE model from a recently published PNAS paper. So excuse me, we have seen, okay, although these models create some difference, and we find they do not agree that well with each other. So for example, if we use the FAIR model, we can see it decrease the raw data, but if we are using the hygroscopic data, it increase the raw data. So that's first the inconsistency we find among models. I have to say, what I'm trying to convey here is not, okay, A model is good, B model is bad. They are all calibrated under a certain circumstances. So they are representing different situations. The only thing we want to show is, okay, when you choose a different model, possibly it will have a different effect on your model, on your conclusions. Second, we want to see what we captured with our sensors. We see that workspace actually show a pretty good and stable air quality. So what's quite astonishing is we find majority of the pollutant events were captured by home sensors. We see that originally, so we at least what I thought was when you finish cooking, possibly after you finish your meal, the air quality should go back to normal. But actually, it shows that's not the case. We see significant peaks associated with cooking aerosols, and more importantly, this did not end in half an hour or even 1 hour. We have seen some peaks last for 3 hours or 4 hours. And if you consider about it, that's create a disparity of exposure among family members. Who is cooking? Usually, at least I'm the one cooking at home. So that means I am exposure to higher level. It should be than my husband, than my kids, right? Then at the same time, we also see a very significant, we didn't show it here, but we see a very significant difference when you upgrade your ventilation system. There was a lady in Pittsburgh that he just updated his home ventilation system, and he want to test. And we basically see very sharp peak in his home. That means, okay, each time when he, for example, start to cook, there is a release. It can be ventilated within 15 minutes. So that's quite good. And also a side note to this work is a lot of homes or houses in Pittsburgh, they don't have a mechanical ventilation system. So you have to open your window to vent all the air pollutants. So then we use the Monte Carlo simulation to connect the exposure with the sensor's response and everyone's activity pattern. And then we compare it with this horizontal line. This horizontal line represents the PM 2.5 concentration we estimated just based on external monitors. We did not include any indoor sensors. And we show, okay, for hygroscopic correlation and also the two-piece correction model, we studied 4 groups of people employed indoors, and school children, someone work from home and employed outdoors. And we see that their exposure level is quite close to the ambient average. But with the EPA correction and the welfare correction, they pull the conclusion to different directions. The EPA correction shows that you cannot be represented by the outdoor average because your exposure is higher than the outdoor average. And with the wildfire correction, it shows, okay, you're pretty safe because your exposure level after considering the indoor pattern is slightly lower than the outdoor average. But another thing we want to highlight here is, can you be represented? For example, if I'm a kid, can I be represented? And I think the answer is no, because we see a very large range of PM exposures. And that means an average for a group of people, even though their daily activity is very similar to you, possibly cannot represent you accurately. So this is what we learned from the Pittsburgh study. So then I want to introduce some of the concerns related to air quality sensors. So first one is the overused machine learning algorithms. Although I'm still a supporter of machine learning algorithms, but I start to think about what machine learning or very complicated calibration model bring to the sensors. Can they actually improve sensors performance? So we all know for your model, if you include more parameters, you are supposed to improve it and get a better R² value or R value. But does a better R value represent a better sensor performance? I think the answer is no. And especially we should be careful about selecting the variables. For example, if we have for PM sensors, we didn't see people referencing a lot of different sensors. But for example, when we calibrate nitrogen dioxide sensors, if we include carbon monoxide sensors, ozone sensors, and relative humidity, temperature, and the sensor response itself, you can get a very good calibration model. But what does it actually represent? Possibly is a historical trend of the relationship between all these air pollutants, rather than it's improving the response from sensors itself. So I think later for calibration model, we should focus more on sensors performance, and especially challenging sensors limit. So we all know there can be so many improvements to calibration model, but where should be the limit of sensors? I think that should be something we should consider. So the second thing is about a sensor management challenge. So sensors, there are so many sensors, and they are creating a lot of electrical waste. How can we identify sensors expiration in the field effectively? I will give an example later. And also, how can we dispose the waste associated with sensors properly? The second one is about a management effort. So when you manage one sensor and when you manage 10 sensors and 1,000 sensors, they are totally different workload, and it's not increased proportionally, and it doesn't decrease proportionally either. So is there a way that we can think about the economical and management effort regarding the sensor deployment? So that's the second thing I think we need to think about. The third thing is it a too hot field? We have seen a lot of publications about sensors recently. Is it possible that we can integrate everyone's effort into a same blueprint so that we are maximize our output based on the research from different groups? So that's the third thing I think will be very interesting to see the discussion in the future. Then I would like to introduce this one. So this is it's not PM sensor, but it's still about local sensors. So the sensors degradation over time, I think, was not discussed thoroughly enough in the current literature. In another word, time was not brought into the calibration model as a variable, which they possibly needs to be considered. So this is a work we published on ACS sensors last 2 years ago. So we can see for new sensors, they demonstrate a quite good linearity with R square equals 0.68. And after around 130 days, although we see a decreased R square value, and we see the shift from their original response range, but still the linearity is there. Your sensor still respond linearly to the reference concentration. So the x-axis is sensor signal and the y-axis is the reference concentration. But we see that after around 320 days, there is no linearity at all. We should not discuss R right now. We should discuss whether it still responds to the concentration. And we find that the nitrogen dioxide sensor degradation is a one-way street. So once it's gone bad, it's never recovered. So that's an aging effect. And it's approximately happened around 1 year. Finally, we summarize this the story we learned is, so originally theoretically there should be an ozone scrubber there, and your sensor should respond to both nitrogen dioxide and ozone, but luckily it scrubbed most of the ozone, so your sensor demonstrated a very good performance, a response to the nitrogen dioxide. But after aging, your ozone scrubber start to go bad, and it can only scrub part of the ozone, and that makes your sensor start to get aged. Then finally, what happened is your ozone and sensor both failed. So no matter whether it's nitrogen dioxide or ozone, it cannot trigger enough response in your sensor. And this only lasted about 1 year. But the sad thing is, you can see how long we did the experiment. We did it for 4 years, but only 25% of the data is reasonable. So later it will be a very, very important issue, how we can detect malfunction sensors and the aging of sensors, expiration of sensors in the field, especially in the large scale deployment. So these are about sensor aging. Another concern about, we go back to PM sensor, another concern about PM sensors, right now we see some objections, and these are two most recent papers that they mentioned. The sensors possibly are not as accurate, as reliable as we think. So will your local sensor respond more to small particles or large particles? I think a lot of us will think, okay, it will respond most to large particles. But based on the most recent study, they think they are most effective to particles between 0.1, 1 micrometer. And then for particles larger than, for example, 2.5 micrometer, due to the truncation error, they cannot distinguish the particle size accurately. So what does truncation error mean? So the forward scattering of your particle cannot be collected efficiently, and this causes the truncation error. The forward scattering portion increase with the particle size. So that means, for example, if you have a 10 micrometer particle and you have a 1 micrometer particle, due to truncation error, they are actually reporting the similar amount of, they generate a similar amount of pulse height at your photodiode. So that's the reason they start to think that Purple Arrow or Plant Tower should stop reporting PM 2.5 and PM 10 in the coarse mode, mass concentration. Then we comes to the question, how capable are sensors? I think, I'm not sure whether you are aware of this, but we usually define 5 categories. And then based on sensors precision error, precision error and bias error, we can assign them to different purpose. For example, for tier 1, the education and information, you does not need it to be very accurate. As long as it's around 50% of accuracy, I think we are good. The second is hotspot identification and characterization. Again, you don't need to be perfect as good as regulatory monitors, as long as it can reach around 30% error. That should be sufficient. And the highest level is regulatory monitoring, and it requires around 8% of the error from your reported data, from your results. And we can see that your calibration model can improve. And for some of these sensors, for example, carbon monoxide sensor and ozone sensors, they can reach a level that you can use them for supplemental monitoring or personal exposure measurement. The requirement for personal exposure measurement is around 15% of the level. So and air quality sensors, where is our PM sensors? PM sensors with a model, you can achieve around 10% of the error. So that's the reason, like it or not, EPA is publishing purple air data for reference. So although there are a lot of concerns related to low-cost sensors, still we think it should be the future of citizen science. And the reason is that provide an opportunity for people who are not an aerosol expert like you guys. They can know what's going on around them, and they can set it up easily, like their television, like their TV or their air conditioner. Then they will be able to know what's happening around them, and more importantly, what they can do to reduce their personal exposure. So that's the reason sensors are becoming more and more important. So that's the last slide of my presentation. I would like to thank Albert Presto, Subu, and Carl Mullins for providing their slides for reference, and also thank my collaborators and from the agencies. Thank you. Go. Yes. Yes. For sample sensors, you cannot see it, right? So they're asking for the sample ramps home sensor. What sort of heating source was considered? So most of the heating resources in Pittsburgh is methane. So that's the pure source. And we do see when you are using electric stove rather than the gas stoves, it improve a lot. The second question is, are these particles from heating source or fumes from food? I personally think it depends. So at the original, when you turn on your burner, we cannot see it, but I suspect when you turn on your burner due to incomplete combustion, you are supposed to see more particles from heating sources. But after you start to cook, you can see more particles from food. I also see from Kevin Risby is how appropriate is PM 2.5 mass as an indicator of air pollution? Do you expect an increased focus on monitoring ultrafine particles in the future as the cost of instruments for smaller size ranges comes down and become more accessible? I do think that will be more and more important. And especially current scale is based on mass, and it does not focus on particle number concentration. But when we talk about smaller particles, there are so many research have shown that they are more toxic, and the size concentration of these smaller particles are supposed to be more important. But the issue is right now I have shown that there are a lot of places even doesn't have a PM 2.5 concentration measurement. So I think still a lot of effort will be poured in the PM 2.5 monitoring system. I have another question from Ayush Argol is, also in this cooking PSD, do you differentiate between solid particles and droplets? No, we don't. Yeah, and I want to also mention that our sensors are not put directly next to the in the kitchen. So it's not in the kitchen. So it's just in the connection. Most of it is in living room. Sometimes it's in the connection between living room and the kitchen. If we do the measurement right next to the cook stove, it's supposed to be much more higher concentration. Okay, that's all questions I got from Zoom. Okay, Paquita.
Yeah, again, deploying more low cost sensors at the same site and more sophisticated aerosol instruments to kind of take advantage of the strength of Earth, like put them at all the GWP sites or EPA more sites. Build on that.
Yeah, that's a great question. Yeah, I can repeat the question. So are we considering deploying more local sensors and cooperate with the monitoring sites and other DOE sites, EPA sites, so we can have a better mapping or estimation input to our model? Yes, we do. And we actually published a paper in 2018 about, because Taiwan, they have a very successful local sensor campaign. And in that paper, we incorporated around 2,000 air quality sensors with local ground, with their EPA sites and also with satellite data. So we try to see what's the best we can get from it. And we do see that we do see they improve the spatial coverage, and if we don't include sensor data, the pollution mapping with only EPA sites is kind of very rough, very, very coarse. But with them, we add a lot of details. But we also see some disadvantages of these sensors. For example, when we see the distribution of sensors, we see they are actually very close to the EPA sites. The reason is, although they don't monitor, but if you are the researcher, you definitely want to deploy your sensors near to the metropolitan area rather than in a mountain. So actually the spatial coverage of sensors overlap quite a lot with the conventional monitoring stations or federal monitoring stations. But a good thing is we do see they capture a lot of local events that's buried in the hourly average of your monitoring data. So that's what we see. And we also see it will be very necessary and interesting to incorporate satellite data. And the reason is they can provide the data one with not a lot of population there. Like for example, Everglades, not a lot of people there, but your satellite can still provide the data there. So they all kind of supplement with each other, and they all deliver our mapping results better. Yeah, thank you. Okay, Michelle, yeah.
Sensors would evolve to actually get tracking like on your cell phone, like everybody's using smartwatches. You feel like small enough to be like running around with everybody.
Yes, that's so Michelle is asking whether the sensors can be small enough so that everyone can wear it. I think that should be the goal of future research. I think later the sensors is either it can detect the smaller particles or it's portable. So even, for example, even if it's not that accurate, but as long as it's portable, it can remind you to turn on your hood when you cook, right? It can remind you to wear your mask when you clean your room. So it will be more close to influence our health and daily routines. Yeah, thank you, Michelle. Sure. So Yiming is asking how can satellite detect the PM 2.5? So satellite detect aerosol optical depth. It's a columnar average, integrate columnar average. So in our paper in 2008, 2018, we showed that local sensors actually correlate much better compared to the regulatory monitoring sets, compared to the correlation between regulatory monitoring sets and satellite data. So it's much better. So I know there have been a lot of improvement to increase the temporal resolution of the satellite data and spatial and temporal resolution of the data. But I think mainly it's about coverage rather than it can have a better prediction to the ground data. We also see some researchers are using, for example, machine learning algorithm to incorporate meteorological conditions and even PM composition to improve the inversion from columnar integration to near ground concentration. I think that should be a lot to do later. Yeah, thank you. Any other questions? Okay. Yes, Ayush Argawa is asking, is there a threshold cost value for a sensor to be considered low cost? Does this vary from country to country as the purchasing power of currencies vary? Yes, I think it should vary from country to country. And when we talk about local sensors, I think we are talking about something below $1,000 in US. And most of the time we're talking about something below $500. But that's just an estimation based on my personal experience. I don't think it represents the all over the world. Yeah. That's it. Thank you. Mm, 下一个是
Yeah, that's good.
OK。
What kind of is that data set? Is that what?
Yes. And we are very comfortable. Because if you think about your data set, I think it's temporal also, which means when you do machine learning, your data
Share the
needs to be
screen.
very similar to the data next to it. And that's the part we need to get over. So when we do this, we break the temporal temporal autocorrelation. And then when we do between, we need to run between the team and test. So usually we kind of break the temporal correlation. Yeah. Just no.
Yeah. Okay, so due to the time limit, let's maybe get started so we can continue this interaction after the workshop. I mean, after the tutorials. Okay, so I will start the third tutorial session, which is about the aerosol instrumentation. But in this tutorial, I will just mainly introduce the aerosol size distribution measurements. right? So in terms of instrumentation, there are so many of them, looking at the physical, chemical, or toxicological properties of the aerosols. But again, due to the time limit, I'll mainly focus on the size distribution measurements. So first, I want to list a few references. So these are the classic textbooks in our field. The first one is Aerosol Measurement, Principles, Techniques, and Applications. So this textbook actually introduced you different types of aerosol instrumentation for measuring different properties of the aerosols as well. And the second one is Atmospheric Chemistry and Physics from Air Pollution to Climate Change, right? So these are the two well-known textbooks in the aerosol field. I also want to thank Dr. Chang Yu at University of Miami and then Dr. Jian Wang at Washington University for sharing their slides in this tutorial session. So I'll start with the size distribution. So as you have heard from Dr. Biswa's tutorial, the size distribution is probably one of the most important parameter, I would say physical parameter, physical properties of the aerosols, right? So if you want to understand the different processes or mechanisms involved in the atmospheric aerosols, let me change the cursor. Right? So if you want to understand different processes, you have to be able to first measure these aerosols in terms of their sizes. For example, if we just look at the size distribution of aerosols in the ambient air, right? So normally people will observe different modes that include the nucleation mode, which we normally refer to the particles with sizes below 10 nanometers, right? So the atmospheric nucleation or the new particle formation is a quite important and also a very, I would say, popular topic in the recent decade, because people show that actually the atmospheric new particle formation can contribute more than half of the cloud concentration nuclei on our Earth. Right? So if we want to understand where these aerosols are coming from, we have to be able to measure particles with sizes below 10 nanometers. And then these smaller sized particles can grow up through coagulation, condensation, or other processes until they're in the tens of nanometer size range. And we call these aerosols as Aitken mode aerosols. And these aerosols can go through further processes that grow up or go through the cloud activation until they are in the hundreds of nanometer range. And we call these aerosols or this mode as the accumulation mode, right? So these accumulation mode aerosols can directly contribute to the cloud condensation nuclei upon activation in the cloud. And we also have particles with larger sizes, let's say in the micrometer range. So these aerosols can be generated from the wind-blown dust or emissions, biological emissions, or sea spray processes. So overall, if we want to understand these mechanisms, again, we need to be able to measure the size distributions of the aerosols. But how do we measure them? I have to say that there are so many different ways to measure the size distribution of aerosols. So to measure their size distribution, we have to separate them into the sizing part and the counting part, right? So the sizing will provide you with the size information of the particles, and then the counting part will provide you with the concentration of the particles in different sizes. And in terms of particle sizing, there are multiple ways. For example, you can collect these particles offline onto a filter grid and then go to like some advanced microscopes, like Sujan is doing some offline characterization using the microscope facility at PNNL, right? So you can look at the size of the particles, but also analyze the chemical composition of these aerosols. And then there are other methods like the optical methods that Dr. Jiayu Li introduced in her talk. But in my talk, I'll focus on these two methods, which are also quite widely used for measuring the particle size. So one is the aerodynamic method, which is using the inertial property of the particles to monitor the size distribution of the aerosols. And the other one is the electrical method, which is using the electrical mobility of the particles to look at their sizes. So further under the electrical method, I'll talk about the electrical mobility classification, the transfer function, and data inversion, right? So there was a question asking, how do we get the DND log DP size distribution? So I'll talk about this briefly, because we need to go through the data inversion to consider all the different factors involved in the particle measurement. And then there are some special needs for particle size distribution measurement. For example, we need to do measurement with high time resolution. You may want to measure size distribution every 1 second or every 0.1 second. We can also develop new methods to measure the particles with very small sizes, let's say sub-3 nanometer particles. So these will involve innovation in aerosol instrumentation. And then apart from the sizing part, equally important is the particle counting part. So people can use electrometers to measure the concentration of the charged particles, right? But I would say a more widely used method is by utilizing the condensational growth of the particles. And then on that, the condensation particle counter is the most widely used instrument for measuring or counting the concentration of the aerosols. And using this condensation method, people can invent new methods. For example, the bio-inspired instruments. And some of these instruments were actually invented by Dr. Chang Yu here at the University of Miami. So I'll just get started first with the aerodynamic method. So the aerodynamic method uses the inertia of the particles, right? So Dr. Biss was talk about the drag force and then the movement of particles with any mass. So one example is that we can introduce some flow carrying particles towards a stagnation plate, right? We call this as an impactor. So because these particles carry certain mass and then they have certain sizes, and then because of the inertia of the particles, they will not be able to follow the flow or the streamline, right? And then due to this particle inertia, they're going to collide onto the stage. And by using the, let's say, the Newton's second law, we can actually accurately predict where the particles are getting impacted onto and what is the size of the particles that are collected by this impactor. And for this inertial impaction process, the stopping distance of the particle is very important. And the stopping distance can be calculated based on the relaxation time of the particle and the flow velocity. And the relaxation time is further a function of particle size, particle density, and then some other parameters. And you can see that the relaxation time is dependent on the particle mass or the inertia of the particles, right? So basically, for each set of the impactor, we can actually collect particles with certain sizes. So this impactor can act as a size cutter that collect particles above certain sizes. And by using this idea, we can tandemly connect all of these impactors with different sizes or cutoff sizes. For example, we can introduce a bunch of particles here. The first stage can collect particles with larger inertia, and then some particles or particles with medium sizes can escape from this first stage. They can go to the second stage, where, well, in the second stage, we can use a smaller nozzle to accelerate the flow, right? And then we can also use a shorter distance between the nozzle outlet and the plate here. So make this distance shorter so we can collect particles of medium sizes, and so on and so forth until the last stage where we collect the smallest particles. Right. By using this method or this tandem arrangement of these impactors is also called as the cascade impactor, which has so many impactors with different cutoff sizes, right, combined. And then I would say a widely used instrument or cascade impactor is called a Moody impactor, which is commercialized by TSI. So in the Moody impactor, they either have 10 stages or 13 stages that has different cutoff sizes. And you can see I would say the first stage has a cutoff size of close to 20 micrometer. And then the last stage, or the 13th stage, has a cutoff size down to 10 nanometer. So you can see it can cover a wide range of the particle sizes. So the impactor can provide us with the aerodynamic size information. Then how do we count it, right? Counting is equally important. So in the cascade impactor, people used to collect the mass of the particles that are deposited on each stage, measure their mass, and then you could derive the mass concentration. So that's a way of counting, right? So if you have the mass concentration, then you know, or you can relate the size with the concentration and then get the size distribution. And then, so here, this is a detailed table showing you the Moody impactor. For example, there are 1 to 10 stage, their cutoff sizes, and then the associated Reynolds number. And then for these cascade impactors, if you imagine for the last stage, where we're collecting very small particles, like 10 nanometer particles, then their inertia will be very small. And because of that, you have to drive a very high flow rate or very high flow speed through the nozzle. But there's a limit for this flow speed, which is the speed of sound, because at that time the flow is going to be choked, right? So since the flow speed is close to the speed of sound, we also need to consider the compressibility of the air. So the calculation or derivation of the cutoff diameter is going to be different compared to the first stage. So that will involve the design of the low pressure impactor or micro orifice impactor. And on this topic, I would have to introduce Dr. Biswa's PhD dissertation, which is mainly focusing on designing high-speed impactors. So you can check those very detailed equations from his dissertation. So we could use the mass to derive the size distribution of the aerosols, and we could also convert the particle concentration into an electric signal. So the way we can do that is we can first charge these aerosols. So this is a schematic diagram of the electrical low pressure impactors, where they first charge these aerosols with unipole charger. And these particles will carry certain charges onto them, and then they will get collected at different stages of the impactor. And the collected charged particles will transmit their charge as a current. And then you can use the electrometers to count what is the number concentration of the particles. So in this way, you can get or count the particles, and then at the same time, you have the size information, and then you can get the size distribution. And then I would say this is a relatively newer technique in the aerosol field. So this instrument is called the aerodynamic aerosol classifier. So this instrument is commercialized by Combustion, right? So the mechanism for this instrument is that we first introduce the aerosols into the gap between two concentric cylinders. While these cylinders, at the same time, they're spinning at a high speed, right? And because of the spinning, you can imagine this analogy as a washing machine, right? So because of spinning, the larger particles or heavier particles will get spun out, while the smaller particles, because they have smaller inertia, they will still follow the streamline, and then they will probably move a little bit distance in the radial direction. But then you can imagine under certain spinning speed or the radial velocity, only particles with certain inertia can get collected, or particles with specific aerodynamic sizes can get collected. And then they can exit through this outlet here and further get counted by some particle counting devices. And one major advantage for this instrument is that it does not rely on the charging of the particles, because I'll show that later on that particles with relatively small sizes, let's say below 50 nanometer, are very difficult to get charged, right? Because their charging probability is low. Then we have to consider the counting statistics, because if a counting device is telling you 1 particle per centimeter cube for a 10 nanometer particle, it may actually mean 100 particles out there, because it's very difficult to charge them. But for the AAC, since it relies on the aerodynamic property of the particle or the inertia of the particle, then they don't rely on the charging. So you're going to collect much more particles, or in this way, you can enhance the counting statistics of the instrument. And then I would say the most widely used instrument for monitoring the aerodynamic size distribution of the aerosols is called the aerodynamic particle sizer, the APS. This is also commercialized by the TSI. So the APS measures the particle size distribution, also relying on the aerodynamic sizes. So it uses 2 laser sheets to detect particles. Although it's using laser, it's not necessarily using optical size of the particles. It's actually using the time of flight of the particles between these 2 lasers. So the mechanism for the APS is that it introduces the particles into a nozzle, and then the nozzle has a very high flow speed, close to 150 meters per second. So in this way, it can create a large difference between the particle speed and the flow speed. So in this way, you maximize the drag force. And because of the drag force, it's going to create the, let's say, the differential movement of particles with different inertia. So you can describe the motion of the particle using the Newton's second law, where on the left-hand side, you have the acceleration. On the right-hand side, you have the drag force, right? So you can see that the movement of the particle is purely dependent on the size of the particle, or the aerodynamic size of the particle. So in this way, by counting the time of flight, you can calculate or you can derive what is the original aerodynamic size of the particle. And one important thing to notice for the APS is that it's almost perfect for measuring solid particles, which are the particles that has very rigid properties. You can see the APS has very high counting efficiency for solid particles, close to 100%. But then if you're measuring liquid particles, you have an issue. This is mainly because liquid particles, if you don't have a high speed of the flow, then they can retain or maintain this spherical shape. But if you expose them to a high flow speed, then they're going to change their shape, right? Instead of being spherical, they're going to get compressed, right? And more importantly, they're going to get shattered or fragmented until they're into the size that cannot be detected by the APS. So you can see that's why when you're measuring liquid droplets, the APS is going to have a lower counting efficiency. And that's why if you're using the APS, it's better to dry your aerosol samples before doing the measurement. So that's it about the aerodynamic method. So here I will mainly focus on the electrical method. Okay, so the electrical method is mainly used for monitoring particles in the submicron range. So the most widely used instrument that's using the electrical method is called the scanning mobility particle sizer. So it can measure the submicron aerosol size distribution basically below 1,000 nanometer, right? From let's say 2 nanometer to 1,000 nanometer. So here are two pictures of the SMPS system, right? You can see this is a newer SMPS system that I believe many of you or in your lab have this system there, right? And then the TSI also used to have an older model of the SMPS system. And of course, there are other companies manufacturing SMPS system too, like the Bertel SMPS, or this is the Pallas SMPS. But if you look at their pictures, they have some commonalities, right? There are something in common. So they all have one component, like big box, right? And then they have a column sitting by them, and then they have a box that's connected to this column. So here I will just use the TSI SMPS as an example. So the big box is called the electrical classifier, right? Which contains the blower system, which is a flow system, right? And then the high voltage system, and then the control system. And then we also have the differential mobility analyzer, which classify particles based on their electrical mobility size. And then we also have a smaller box that is a condensation particle counter, which counts the concentration or number concentration of the particles. So if you think of the particle sizing, then the DMA is the one that's playing the most important role. That's classifying the particles based on their electrical mobility. So you can imagine DMA as two concentric cylinders again, right? Except this time they're not spinning, right? So the inner cylinder is connected to certain high voltage, and the outer cylinder is connected to the ground. And then the aerosols are being introduced from the side of the outer cylinder. At the same time, we have a clean sheath flow, particle sheath flow that are being introduced from the up to the down. And normally people use a relatively high ratio of the sheath flow to the aerosol flow, normally 10:1. For example, if you use 1 liter per minute of the aerosol flow, then you'll introduce 10 liter per minute as the sheath flow. So you can imagine if you're a particle, then because of the sheath flow, they're just going to get brought downwards, right? But now if we pre-charge the aerosols and at the same time connect the center electrode to certain high voltage, and then these charged particles will start to move or migrate towards the center electrode. And under certain high voltage, only particles with specific mobility sizes can get classified. And now things are getting simple. So since 1 voltage corresponds to a specific size, you can just scan the voltage on the center electrode, right? People will normally scan it exponentially. And then since you already have the classified particles, you can directly send it to a particle counting device to get the number concentration. So by scanning the voltage, then you can get the concentration particles with different sizes. Then you're going to get the size distribution. So this is the basic mechanism of the SMPS system, right? So this is another schematic diagram of the SMPS system. So you have some ambient or random aerosols coming from, let's say, the ambient environment or from any aerosol reactors, from diesel engines and so on. So we will first charge them with a unipolar charger. People prefer unipolar charger mainly because these chargers are more certain or more well quantified in terms of the charging efficiency. So after these particles are charged, we assume that many of these particles are singly charged, right? And then they're exposed to the gap between the inner cylinder and the outer cylinder. And then at this time, you can start to separate the particles. And because these particles are charged, then it involves a balance between the electrostatic force and the drag force, right? So the electric field is going to pull the particles apart. And the smaller particles are going to move faster compared to the larger particles. I'll show you why that is the case later on. But under certain voltage, only particles with certain sizes can get classified. And then you get particles with monodisperse size distribution, and then send it to a condensation particle counter or electrometer, where you can count the number concentration of these specific size particles. And then by scanning the voltage on the DMA, you can get the size distribution, right? This is a mechanism of the SMPS. So since we talk about the electrical mobility, right? Or the electrical method, we first need to understand what is the electrical mobility. So the electrical mobility is defined as the ratio between the migration velocity of the particle over the electric field strength, right? So because under high field strength, the particle will move faster, lower field strength, particle move slower. So the electrical mobility has to consider that and normalize it by the electric field strength. And further, since you know this velocity here, you can calculate what is the drag force of the particles under the or inside this DMA here. So you can directly equate the electrostatic force with the drag force, right? The electrostatic force is just a QE. The drag force, as Dr. Biss was showed in his slides, is 3 pi mu dp multiplied by V, which is the velocity of the particle divided by the Cunningham slip correction factor. So you can see, basically under the same electrostatic force, then particles of different sizes will have different velocity, right? Because if we assume that most of the particles are singly charged, then they have the same electrostatic force. Then smaller particles will have larger migration velocity. Larger particles have smaller migration velocity. So because of that, since these particles are exposed to the same field strengths, then smaller particles are going to migrate faster. So that's why they're getting classified first, while larger particles will get classified later on, right? So because of that, only certain, when you have certain voltage applied onto the DMA, only particles with specific sizes can get classified. And further, inside the DMA, we have this relationship that can build up, right? So on the left-hand side, that's the mobility of the particles that are getting classified. On the right-hand side, this is related to the flow configuration of the DMA. So QC and QIM are the sheath flow, inlet and outlet of the DMA. R2 and R1 are the inner radius and outer radius of the DMA, right? That are shown in here. We're talking about the radius of the columns. And then for pi, these are constants. L is the length of the classification zone. And then V is the voltage being applied onto the DMA. So you can see that under certain voltage, only particles with specific mobility are getting classified. And at the same time, the mobilities has a one-to-one correspondence with the particle size. So that's why when you have certain voltage, you're going to classify particles with specific sizes, right? So here I'm showing you the one-to-one correspondence between the electrical mobility and then the particle size. You can see across different sizes, then you can have, let's say, when the particle size increases, then the mobility is going to decrease, right? Because the particles are getting less mobile. And then the electrical mobility also depends on the number of charges being applied onto the particles, right? So if the particles carry more charges, then they're going to be more mobile under the electric field strength. So basically, this can sometimes cause some multiple charging issue when we're trying to collect particles of different sizes. I'm going to talk about the multiple charging correction later on as well, right? But here you can see that overall, if you have particles of specific size, and if you know the charge on the particle, then you're going to only have a single electrical mobility. So now let's get back to the DMA, right? So this is showing you the schematic diagram of a DMA system again. You have the center electrode, you have the outer electrode. You can separate particles based on their sizes. Smaller particles get separated faster, larger particles get separated slower. And then for the TSI DMA, they also have two different configurations. They have the longer DMA, which normally people call it as a long DMA, and they have the shorter DMA, which people call it as a nano DMA. So for these two DMAs, if you check their radius, they're all the same, except that their classification zone is different, right? So the length is different. This is mainly because the long DMA is responsible or is being used to classify particles with larger size ranges. So if you check the configuration or the manual, the long DMA can classify particles between 10 to 600 nanometers, right? That's mainly because larger particles close to 600 nanometer, they're difficult to get classified. That's why you need a longer distance to classify them. Well, for the nano DMA, you don't need that long of a distance, so you need a shorter classification zone. So this can explain why different DMA configurations or lengths can be used to classify particles of different sizes, while the nano DMA classify particles between 1 to 100 nanometer, right? So there are also other different configurations for the DMA. We're talking about the cylindrical DMA. They can also be parallel plate DMA, right? So this is one of the parallel plate DMA, but people call this as a radial DMA. So this is first designed by Dr. Rick Flagan at the Caltech group, right? So in the radial DMA, so the method for introducing the aerosol is actually to introduce them in a circular region, right? So in this ring region. So the particles are also charged, while the sheath flow are being introduced from the top. It's also being introduced by this circular manner here. And then you can apply certain voltage onto this top plate here. So you can imagine the particle are going to get attracted, right? And then further get classified. Well, particles with the wrong mobility or particles are not charged, they won't get to the exit here and they'll get transported through the sheath outlet here, right? So in this way, you can also separate the particles based on their electrical mobility, except here, now you don't have this very long configuration of the DMA. So you have a very flat system, and this system can be very lightweight as well. So people call this as a radial DMA, but there are also modification to the radial DMA that now, since you need to introduce the aerosols in a circular region, you also need to introduce the aerosols at different locations on this ring here, right? Because if you just introduce aerosol on one part, then you're going to have a misdistribution of the flow, and then the classification is not going to be ideal. So that's why they can introduce the aerosols through these tubes into this circular aerosol inlet. And at the same time, we need to make sure that the particle transport laws are the same at these different regions. So that's why when you're introducing aerosols into this location, you have to create a longer transport channel for these particles. So that's why it creates this shape, looks like a spider, and people also call this as a spider DMA, right? So the spider DMA can be then combined with different CPCs. For example, in Dr. Wu's group, there are 2 spider DMA or spider magic CPC SMPS system, right? So you can take a look during the lab tour tomorrow. So overall, this can reduce the weight of the DMA system and the entire SMPS system. So if you have a real TSI SMPS system, if you try the weight before, it's close to like 20 kilograms or at least like that. But for the Spider Magic SMPS system, the weight is close to 4 kilograms, which is very light. Okay, so now I will talk about, or briefly talk about the transfer function and the data inversion. So the transfer function has to be considered no matter which instrument you are talking about. We introduce the impactor, introduce the aerodynamic particle sizer or the APS. We all need to consider the transfer function. So the transfer function, especially for the DMA, is designed or defined as the probability that a particle of mobility ZP will be transmitted from the aerosol flow to the monodispersed sample flow. So basically, it's a probability of particle with certain mobility that are able to go through the inlet to the outlet of the SMPS or of the DMA system, right? So you can imagine if the DMA is set up to classify 100 nanometer particles, then most of the particles won't get classified. So their probability is 0. But for 100 nanometer particles, their probability will be close to 100%. But what about 99 nanometer particle, 98, or 101 nanometer, 102? right? So are their probability 100% or 0%, right? So this involves the consideration of the transfer function, where we have to calculate the probability of particles that can get transmitted as a function of their mobility. So in terms of the derivation of the transfer function, I recommend you to read this classic paper by Nelson Whitby, 1975. You can see how the complex problem of the transfer function of this cylindrical DMA can get simplified really elegantly into the conservation of the streamline. So the derivation of the equations are also not difficult. As long as you have some high school physics background, you should be able to derive or look at really how the transfer function is so simple in this system or the DMA system. Okay, but simply speaking, when we talk about the transfer function, right? So again, using an example of classifying particles of 100 nanometer. So you can imagine if we introduce 100 nanometer particles, then they can get perfectly classified, then all of them can get transported through the exit of the DMA where the aerosols are getting classified. But then for, let's say, 99 nanometer particles, so these 99 nanometer particles are smaller. So their migration velocity is faster, as I showed earlier. So their trajectory is going to move up, right? But you can't really say that all of the 99 nanometer particles are not getting classified. There are going to be some proportion of particles that can still be able to get classified and then exit through this aerosol outlet. And then for 101 nanometer particles, these larger size particles, it's also possible that these particles can get classified. And again, from this Nelson-Whitby paper, it showed that actually the transfer function of the DMA looks like or has a triangular shape, which means that at the centroid mobility where you set up the DMA, it's going to have a 100% collection efficiency, while the transfer or the probability is going to decrease linearly as a function of their mobility. So you really have to consider the mobility of the particle instead of the size of the particle, right? So, and further, this transfer function here has certain resolution, right? So people really want these narrow transfer function because you want to be accurate in terms of particle sizing. But then in the derivation, it shows that no matter which DMA you are using, there's always going to be some width associated with the transfer function. And people design or define the resolution for the transfer function, which is the centroid mobility divided by the half width at full width at half maximum of the transfer function. And people find out that the resolution is just the ratio between the sheath flow and the aerosol flow. For example, if you use the sheath to aerosol flow of 10:1, right? Then in the transfer function, it's going to have a resolution of 10, which basically means that the width of this peak here is going to be 0.1. All right, so this is the transfer function. So why is it important that we need to derive this transfer function? So for example, you set the DMA to classify 100 nanometer particles, again, using this size here. And then you have the CPC downstream of your DMA, and then the CPC is giving you 100 particle per centimeter cube. That's a concentration. So can we say that the concentration for 100 nanometer particle is exactly 100 per cc? No, right? Because for this concentration here, it's going to have particles of smaller sizes and larger sizes. But more importantly, there are also other processes involved in the particle classification counting. For example, there's charging efficiency. As I mentioned earlier, not all of the particles are getting charged. There's always some proportion of particle, let's say 100 nanometer particles are being neutral or being negatively charged, right? So they can have different polarity. So we're only classifying particles that can get attracted, not repulsed or not neutral. So you need to consider charging efficiency. You also need to consider the penetration efficiency of the particles because they can get lost while they are being transported in the SMPS system. We have to consider the transfer function because particles of smaller sizes and larger sizes are also getting classified. And we need to consider the counting efficiency, the CPC counting efficiency. For example, when we're using CPC to measure particles down to 3 nanometers, then these CPCs will have challenges to measure these very small particles. Then there's a counting efficiency getting involved. So we have to consider all of these processes in order to obtain or to understand what is the real size distribution of the particles. So in addition to this discussion of the transfer function, right? So in the Newton and Whitby paper, they did not consider the diffusion of the particles because as we know, when the particle size are getting smaller and smaller, then the bombardment onto this particle is going to create this random motion of particles, right? So then when the particles are getting classified, then because of diffusion, they're also going to deviate from their original or theoretical trajectory, which means that when you're trying to classify even smaller particles, then you're going to be even more inaccurate when you're trying to measure them, right? And a direct example is that when we're trying to use the TSI long DMA system and then classify particles under different voltages. And for these voltages, the larger voltage will correspond to larger sizes and smaller voltage correspond to smaller sizes. And this is showing you the transfer function, right? So when you're classifying larger particles, close to hundreds of nanometers, then you're going to get an ideal triangular shaped transfer function. But when you're trying to classify very small particles, let's say close to 1 nanometer, you see how broad this transfer function is, right? This is because of the Brownian motion of these particles. We need to consider these inaccuracies when we're trying to derive the accurate size distribution of the particles. So this is the charging efficiency of the particles. You see the charging efficiency is a function of the particle size. When we're dealing with particles, let's say below 50 nanometer, then their charging efficiency is also getting lower. For example, if you're looking at particles carrying +1 charge or -1 charge, if you look at, let's say, 50 nanometer particle, then only 10% of them are getting charged, right? The rest of them are getting, are being neutral. And when you're looking at 1 nanometer particle, you see their charging efficiency is even lower. It's below 1%, right? Which means that if the CPC sees one particle downstream of the DMA at 1 nanometer, then it means that there are actually 100 of them outside, right? Charger is very inefficient to characterize or to charge these particles. So to consider all of these mechanisms in measuring the size distribution, then we have this equation. So now you can understand that what the CPC really shows you is just the response, or it's just a cluster or ensemble of particles with different sizes that are subject to different mechanisms, right? The mechanisms include the particle penetration efficiency, the counting efficiency, the charging probability, and then the DMA transfer function. And of course, the size distribution, which is unknown, also play a role here. So you can see the response of the DMA is going to be an integral of all of these different processes. And our goal, or at least the goal of the PSI or those software, is to try to calculate what is size distribution based on the CPC response, right? So there are different methods for this process to calculate the actual size distribution, and we call this process as the data inversion. So the first step is to split or break down this integral to different size bins. And you can make these size bins very narrow, right? So in this way, you can get more accurate size distributions. And then assuming that the size distribution is radically constant in these different efficiencies, right? So if you, let's say you can have different efficiencies of the charging or of the transfer function, but if the concentration of particles are radically constant in this narrow window, then you can pull this concentration outside of this integral sign. You can treat that as a constant, right? So now instead of integrating the size distribution inside this integral sign, you pull that out. So now this calculation is getting converted into the algebraic addition, right? Well, at this inside the integral sign is a transfer function, counting efficiency, let's say the charging efficiency, and then the transfer function are all known properties. So now the problem converts into, well, you have CPC measurement at different voltages. How do you get the size distribution at different sizes? You can do the measurement at different voltages, right? And this gets into a matrix calculation. So you have responses at different voltages. You're trying to calculate the size distribution at different sizes. And then here, this is just the integral that we show here, which is a known parameter. So the data inversion gets converted into the matrix calculation. And there are previous studies or different mechanisms to do this mathematical inversion here, right? So there is this well-known Toomey inversion method. I believe the TSI is using Toomey or advanced Toomey inversion technique. And there's also this non-negative least squares matrix method, which is the Lawson and Hansen method. It's using the L shape or L curve to derive the size distribution. So basically it shows that, well, the size distribution is more than the data you obtain from the TSI AIM software, right? So every time when we run the SMPS, you see a nice curve there, but actually there are different mechanisms getting involved in this data inversion or this measurement process. So after this transfer function and data inversion, I want to briefly mention some other needs regarding the size distribution measurement. And one is a measurement with a high time resolution. So if you go back to the SMPS measurement, if you operated that before, you will see that, well, the SMPS needs a scanning feature. And normally the scanning will need at least 1 minute. So their newer model said that they could finish the scan in 30 seconds, which is huge improvement. But if we're trying to look at some processes with very transient aerosols, then we may have a problem. So one example is the combustion process, where we know that the ignition and extinguish process is very transient. We can generate smoke that's very different compared to the steady state burning condition. And then people also put these systems to monitor the aerosol size distribution on the research aircraft. And we know that these research aircraft move with very high speed, close to 100 meters per second. But if the SMPS needs 1 minute of scan, then the aircraft is already 6 kilometers away, right? This low time resolution is getting translated to a low spatial resolution. So basically, we need instrument that can do these high time resolution measurement that can achieve 1 Hertz measurement. And also want to make sure they have accurate capability of measuring size distribution, especially below 100 nanometer. So there are existing or well-established commercialized instruments to do that. For example, the TSI EAPS, FMPS, and then the combustion DMS 500, which are using these DMA methods to classify particles. Let's say smaller particles classify first, larger particles classify at the end. And then you have different electrometers to collect the signal of the particles and then get the size distribution. But then there are issues associated with these electrometers because they cannot measure very low concentration aerosols. So the counting statistics are going to be low. So for example, if you want to measure the aerosol size distribution here in Miami, near the beach, where the air quality is very good, then you may need to accumulate, let's say 10 minutes of signal to get a size distribution. So basically, this is still going to be time consuming, but we want very fast measurement, right? So one solution for this system is, I would say, that I have participated in during my postdoc research is to develop this instrument called the Fast Integrated Mobility Spectrometer, or the FIMS. So the FIMS is composed of 2 parallel plates, similar to the DMA, where you have 2 parallel cylinders. And then for these 2 plates, so you have a high voltage connected onto this outer plate here, and then the other plate is grounded. And then you introduce charged particles into the gap between these 2 plates, and then smaller particles get classified first, larger particles get classified slower, same principle, migration, velocity of the particles. And then after that, you introduce them into a low temperature condenser. So basically here from the top, we also introduce this sheath flow, but the difference is that although it's particle free, we saturate it with some alcohol. So we use heptanol to saturate this sheath flow here. And then because of the lower temperature, then these alcohol are going to condense onto these separated particles and grow them into supermicron droplets. And in this condenser here, both of the plates are actually grounded, so they won't move in their horizontal direction. And then at the bottom or at the end of the condenser here, we have a laser sheet to shine across this gap here. So any particles grow into droplets, you can illuminate them and then see them from the picture that's taken by this high-speed CCD camera. So the camera takes picture every 0.1 second. So you can get the pictures or 10 pictures every 1 second. So now if you look at this system from this angle here, this is an animation. We charge the particles first, they pick up different charges, and then smaller particles move faster, larger particles move slower, then they grow into droplets. And then in the image, we're going to get the size distribution information because the location of these particles depend on their electrical mobility because we're pulling these particles apart. And further, as we know, the electrical mobility depends on particle size, right? So the location of the particles can be translated into the particle size. And then how many particles we collect at this location is related to the concentration of the particles. So for example, here we're introducing particles of exactly 100 nanometer particle into the system. You can see that they align on a straight line here. So basically from the image here, you can see, well, this is a video that's combining these different pictures here. You may think these particles are going upward or downward, but actually they're going across, going through the screen because the camera takes picture from the bottom, right? So every time if a particle goes through this plane here, they get illuminated. And then the number of particles getting recorded on this image is related to the concentration of the particle. So we tested this instrument against the SMPS, and you can see this instrument agreed pretty well with the system. But the difference is that the FIMS can measure particles every 1 second. It's much faster compared to the SMPS. And then we deploy this instrument onto the research aircraft to look at the ambient aerosols. And you can see the integrated size distribution agree very well with the total concentration measured by the CPC. But the difference is that now we can get the information on what is happening over a few seconds. For example, here you see these spikes of particle concentration, but they also happen within a minute, right? With the SMPS system, you won't be able to see that unless the aircraft are just stable or stay at that location. But that's not possible. But from the FIMS, you're able to see what really happened during this short period of time and show the size distribution over there. So another need regarding the size distribution is about measuring very small particles. So for these very small particles, as I mentioned earlier, they have Brownian diffusion, then the transfer function is getting much flattened. For example, if you're trying to classify 3 nanometer particles, then particles as small as 2.5 and as large as 3.8 are all getting classified. So in this way, we can't really measure these particles accurately. But one way to reduce this diffusion effect is actually quite simple. That is to shorten the time for the particle to stay in this classification zone. If you give it a shorter time, then it has shorter time to diffuse, right? So in this way, the measurement is going to be more accurate. To create a shorter time, then you need a large flow rate. So that's why there are these newer designs of the DMAs that use high sheath flow rates, and we call these DMAs as high resolution DMA, which normally use sheath flow rates higher than 200 liter per minute, as opposed to SMPS system that has sheath flow below 15 liter per minute. So we can use this system to examine the new particle formation process. For example, this is showing you the comparison between the high resolution DMA and the nano DMA, and you can see, you can clearly track these peaks related with different chemical compositions. And then we use this system to study combustion particle formation. And again, you can see very clearly defined peaks during the particle formation, right? And then the size distribution also agree with these offline measurement techniques, which are showing particles below 2 nanometers. So that's it about the particle sizing. I know I have limited time and I have to wrap up regarding particle counting. So here I will just mainly introduce the condensational particle counting, which is the widely used instrument for measuring the total concentration of aerosols. So for these CPCs, or condensation particle counters, they're using the mechanism of condensation. So we see condensation everywhere. Or you can, if you come from the northern states, right now it's quite cold, right? So if you have the AC on in your home, right, or the heating on in your home, then you can see the condensation or these droplets on your window. And this is because there are tiny aerosols or like uneven surface on the window, and the water vapor start to condense onto these uneven surfaces. And the same thing applies into our daily life. For example, the smoke or this I would say this mist or fume formation out of the stack. This is mainly because inside the stack, you have very high temperature, right? And also a high concentration of water vapor. And once it's emitted into the ambient air, the temperature gets cooler, and then the water vapor start to condense onto those pollutants or PM in the smoke. And similarly, this is how the cloud is getting formed in the atmosphere, right? So you have aerosols rising up. At the same time, the temperature cools down and the water vapor start to condense onto them, and you form cloud droplets. So if you want to understand this condensation process mathematically, then there are actually equations to describe this process. So you can actually solve the concentration of the water vapor surrounding any spherical particle, right? And then you can, by deriving or by calculating, or by solving this differential equation, you can find out what's the concentration of water vapor at any location in this spherical system. And then using this concentration, you can derive what is the condensation rate onto any spherical particle, right? This rate can be shown in here. And once you have the rate, then you can relate that to the volume growth of the droplet, right? Because the condensation rate just brings the extra vapor or the liquid onto these particles. So on the left-hand side, you can see this is a dV, dVp dt, that's the rate of change in the droplet volume. On the right-hand side, this is condensational rate. So you can see that the increase of the particle volume actually is proportional to the size of the droplet, right? So the larger the droplet, the larger the volume, or the faster the volume grows. But at the same time, for a spherical particle, you can write this out. That's pi over 6 dp to the third. And then after you derive that, and you can see that ddp, which is the increase of the particle size, is inversely proportional to particle size. So it means that the larger the particle grow, the slower the size increases. So what is the implication on the condensational growth, right? So basically, here is a simple calculation example. So we don't have time to do the homework here, but you can feel free to derive these equations and calculate that. But basically, if you have two particles of different initial sizes, 0.1 micron and 1 micron, and you can see that under the same supersaturation, under the same duration of growth, both of them will grow to the same size, 57.7 micrometer. Basically, the condensational growth actually grow all of these particles to a similar size. And that's why if you look at the cloud droplet sizes are going to be relatively narrower compared to the aerosol size distribution, right? If you show that in the log normal scale, then normally the cloud droplet size distribution is much narrower. So basically, the implication is that in the condensation system, particles grow to the same size or almost the same size, regardless of their initial sizes, if there's sufficient vapor for the particle size growth. And we can use this method to actually to monitor the concentration of the aerosols. For example, you can introduce particles of different sizes, but eventually after condensational growth, they're going to have a very narrow size distribution. And in this way, basically you can expose the aerosols under the, let's say, first the saturated or high temperature region, and then cool that down. The vapor is going to grow the particles to almost the same size. And then you can use a laser to detect the particles, because now you have supermicron droplets, and then it's easier to detect them, right? So basically, if you want to measure the concentration as a function of particle size, then if you don't grow them, there are different scattering principles, right? The Rayleigh scattering principle, the mean scattering principle, which can get quite complicated. But once you grow them to the same size, it's much easier to count the particles, right? So basically, you cannot use a CNC or CPC to measure the size distribution, but you can combine that with a DMA, where the DMA classify particles of specific sizes, and the CPC measure the concentration of those sizes. We could also use the condensation method to generate particles of similar sizes. For example, you can use a nebulizer to generate particles of different sizes, and then to evaporate them and further condense them. And since they grow to the similar size, then you can get almost monodispersed size distribution of particles. You can use this method to actually create functional nanoparticles that have similar sizes. And then for a lot of these condensation particle counters or CPCs, they use alcohol as a vapor to count the particles. But what about water? So technically, we could use water to condense onto aerosols. And that's why we see this cloud formation or see the water that's condensing onto our window. But alcohol CPCs actually don't work with water. And this is mainly because water diffuses faster than heat. So one example is that if you use alcohol CPC and then expose it to a colder environment, then since the heat diffuses faster, right? So you're going to create a colder region in the center, while the alcohol vapor won't be able to diffuse very fastly. So you're going to create supersaturation here. But then if you have water here, then water diffuse faster compared to heat. So you're going to have less or less vapor to grow the droplets. So you cannot really grow the particles into droplets. So that's why, I can skip one slide over here. So that's why when people are designing the CPCs associated with water vapor, they actually use a hotter region to condense water vapor onto the particles so they can grow into supermicron droplets. And then by using this similar method, we can get inspired by some biological applications. So here I'm showing you a system called the Viable Virus Aerosol Sampler, the VIVUS, right? So this system actually uses water condensation to collect virus aerosols. So during the COVID-19 pandemic, a lot of aerosol studies actually collect these bioaerosols and try to see whether there are COVID virus in there. But if you collect them onto filter, these viruses are already inactivated, right? But by using this water condensation method, you could actually condense water vapor onto these virus aerosols into droplets and collect them softly into a liquid. So in this way, you can even detect viable SARS-CoV-2 virus from the system. And this VIVUS system is actually created by Dr. Wu here in CAST. And then you could also use a similar method to look at the toxicology of the aerosols, because people are always talking about the health impact of the aerosols. But after aerosols are being inhaled into our lung has high supersaturation, a lot of vapor. They're going to grow onto these particles, right, to form droplets. It's a similar process that's happening in the condensation or in the system that I showed earlier, right? So you could use the same method to grow them into water droplets. And in this way, this is a more engineered way to deposit these particles onto the cells, so you can study the toxicology effect of the aerosols. So compared to the conventional deposition systems, like the cloud droplet system that's manufactured by Vitrocell, so this condensational method or this David system can monitor the dosage of the aerosols more accurately. While for the Vitrocell system, as you can see, it's generating particles in the form of mist and then settling the particles based on gravitational settling, right? So you don't have a necessarily even distribution of the aerosols. Well, for the David system, you can really control the dosage onto the particles. Okay, so that's it for my tutorial. I think I covered many things very quickly. But overall, we discussed the particle sizing and particle counting. And then particle sizing, we talk about the aerodynamic method and electrical method. And then in counting, we mainly focused on the condensation method and then talk about some innovative designs for the instruments. Okay, so that's it for my tutorial. And feel free to ask any questions. Yeah, so I see two questions here. So first question is, for sizing user inertia, is it possible to measure a mix of particles having different composition or density? Is it densities of, or is this suitable for homogeneous particles only? No, it actually collects particles based on aerodynamic sizes, right? So particles of different chemical composition, they may have the same aerodynamic size, right? The impactor cannot differentiate particles with different chemical composition. So the second question is there any sum rule to define bin width during data inversion? Is there any limitation to the fixing the lower limit of the bin width? So this question is talking about the data inversion, let's say the bin for the size distributions. Let me go back to this slide. Right? So regarding this bin width, of course, if you want to get a very accurate size distribution, you want finer bins, right? Because the assumption is that the particle size distribution doesn't change much in this small bin here. But the thing is that if you have too many bins, then that will involve too many size distribution to derive, which on the other hand, if you look at the data inversion, to get a sufficient number of size distribution, you need to get a sufficient number of the concentration, right? Which means that the SMPS has to scan for many bins and then fix that at that bin for a long time to collect sufficient particles. So this will take a longer time for the measurement, right? So I would say right now, many of the size distribution measurement, they either use 32 bins or 64 bins, because that should be sufficient for most of the ambient aerosols, because ambient aerosols are relatively broad enough. But if you're talking about, let's say, particles with very fine size distributions, then you want to increase to decrease the width of each bin to get a accurate size distribution. All right. Yes, Bindu. Yeah, so you're talking about the surface tension in terms of particle counting, right? The CPC. So correction for factor for the Kelvin effect during condensation. Yeah, so I think that's considered during the condensation or the CPC counting efficiency, right? So the counting efficiency here. So that's why when the particle, let's say the most, or the CPC that has the smallest detection size for the TSI CPCs can go down to 2.5 nanometers. So if they're below, then you can't really say for sure what is the accurate concentration of the particles because the CPC can't detect them. But once they are activated, you can see from these condensational rate equations, they actually grow to a sufficient large enough that you can't really differentiate them in terms of the droplet size. So basically, it's kind of like once they're activated, you can sufficiently or comfortably detect all of them. Yeah. Yeah. Very good. I think we're really running late. So let's still take a 2-minute break, right? In case you take some water or. Yes, I mean, get your slides. So who'll go first? You go first?
No, that's him.
Yeah.
This I still have 61.
Yeah. I'll remind you.
And then I have about 30 hours. That's mine.
Yeah, get the Zoom, keep it open. Yes, share the screen. Here's the screen. Go to this mode, escape. Then here, share the screen. Yeah, now we should do.
Is mine open as well? So just to switch easily.
Let's see. Yeah, it's over here. Yeah. But I think
It's not there.
no. So right now we're just sharing that screen.
Oh, okay.
But after
So
you
you
finish,
said it.
yeah,
You'll
yeah,
set it up.
yeah,
Okay, all right. Yeah,
okay.
because I'll get confused. With
Yeah,
that.
yeah.
I thought we'll put it on there.
Good.
So let me see. It's over here.
I thought like it's very different, my talk. So
Yeah. He's up now.
yeah, he's
Okay.
up now. We'll go over
Too
from that.
many equations.
Yeah, too
Yeah.
many
No more.
equations. Yeah, no, why not
I
no
had some.
equations? And then
Then-
we'll end with no equations with mine. It's time to discuss the rest.
Yeah, I am going first.
Oh, you're going first anyway.
Yeah. Maybe 21. 21.
Still there,
Yeah, still there.
somewhere international.
Yeah, yeah, the time zone,
Yeah.
maybe early morning.
Early morning. Okay, this is the last one. Okay, we'll get started. Thank you all for coming. Thank you for those who are online. This should be a relatively more fun tutorial session, though I will, of course, we love our equations, so there are still equations. And I have my colleague here, Dr. Amin. He will talk of some very nice applications of nanomaterials, nanoparticles. Okay, so we'll talk about nanoparticle technology and then also discuss the formation of particles. Growth was already discussed, so I'll skip through. There are many applications. I won't go through these. I'll just turn over to my colleague He'll talk about consumer products and cosmetics. So you will see this is such a rich field and so many different applications. And this session mainly focuses on useful applications of particles because it's getting late. Both those are online. I know there are some international folks. And here we are looking forward to our happy hour, right? So just stay awake a little longer and let me see. So nanotechnology is everywhere, right? Impacting us, correct? So we will start early on in the morning. You all woke up. You took a little nap here too. That's okay, but let's go back. So you get out of bed. Your sheets, you miss it right when you get up. It's very soft. It is stain-free. That's due to nanoparticle technology. Very likely some of the particles were made by even aerosol techniques. Okay, so remember that. Please look up sheets, stain-free clothes, and things like that. Then you take a shower. You will hear about cosmetic products, consumer products rather, shampoo, soap. Some of you put makeup, you wear pants. These are all nanotechnology driven. Okay, so please think about this. Particles are everywhere. Can't avoid them. You open your fridge, you drink some milk, cookies. I talk about cookies being crisp. You don't want soggy cereal, right? They add some very small, now you're eating nanoparticles. They keep the cereal and the cookies crisp. And even the milk, look up the milk carton, right? You'll be surprised. And of course, the refrigerator has many nanotech components these days. You want to make them energy efficient and all kinds of things. Then you go into your car, lot of nanotechnology. Of course, in the good old days, there was something called nanopod or iPod. It's gone now. So that, of course, has nothing to do. I mean, it might have electronics to do with nano, but the car has a lot of nanotechnology components. Okay, so you see how much we are just coming to work as yet. And then you come to school and work. Many of you have your laptops, cell phone, example of nanotechnology, right? So ventilation system, if we use some very fancy air cleaning systems, clean water systems, lot of nanoparticle technology based system. Then you go home, we will go for happy hour. You want to watch TV, you play video games, lot of nanotech components, right? So from waking up in the morning, sleeping to all the way, it's around us. So we better understand. And then you are listening to my great nanotech lecture. Okay, so thank you for listening. And I'll tell you some. Now we have to get serious. Why are these all over? Why are they so interesting? So look at a small particle. And now I'm really going down in size. So look at those numbers. You heard about 2.5 micrometers. Those are huge in our nanotechnology world. All the way down to 1 nanometer. Okay, 2.5 micrometers is 2,500 nanometers. And I told you particles are made up of molecules. Okay. They're made up of a stable cluster of molecules. How many of these molecules are in the outer layer? Of course, you can do very precise calculations, but we'll just assume it's uniformly distributed. We'll assume they are spherical in shape, the molecules now. And you can calculate how many are in that outer layer. So as I reduce the size, you see that the fraction, percentage of molecules in the outer layer goes up very significantly. Why is that important? These molecules now can interact with the environment, right? So if I want a certain application, I'll just pick if there is a chemical reaction on this surface, most of my molecules are outside. And of course, there are quantum effects, Newtonian mechanics, which we talked about, drag force. We also talk about those when we do small particle calculations, but they just break down, right? So because these molecules are all interacting, so very interesting. and they give it unique properties. So if I start with a 2500 nanometer particle, same composition, and reduce it to 1 nanometer, it will have different properties. What different properties? It could be optical properties, scattering properties. It could be chemical characteristics. It could be magnetic properties. We talked about charging. So all of these, and I can play with this. So if I can control the size and I can really make these, and there are a lot of faculty here who make these particles and put it to many good uses, and you'll hear about some of them today, right? It's not new. Go back to 4th century BC. These Greek guys did everything, right? No Greek origin folks here, or if you're there, feel proud. They could take gold and make it in different sizes, and the color of gold changed. And when the color of gold changed, it's also an inert material. They like to make all kinds of paintings. You could get different colors, these vases on the ceilings. So when you go around, see some of these old buildings, you're seeing nanotechnology at work done way back. So very fascinating. But today we can make these very precisely. We can make novel membranes. We can get different shapes, different compositions, not just gold, carbon-based materials. This is a picture of different types of carbon-based materials. In our own lab, we play with graphene. We crumple graphene, and we use it as a support. And I'll talk about some applications. I mentioned it in the earlier tutorial, okay? But they're all over. And we don't forget that they could be around here, and I could be inhaling them. They come from combustion sources. The key message is they're all over. Of course, I want to intentionally make them, but they also happen to be in the ambient environment. We heard quite a bit about it. How do you measure them and things like that, right? So I'll just say, and then they transform in the atmosphere. I'll just skip through. We hear about COVID, the SARS virus, influenza virus, protein fragments. These are naturally occurring. They're all in the nanometer size ranges. And then, of course, I intentionally make carbon-based materials, carbon dots, quantum dots, and so forth, right? So many, many different applications. I'll quickly go through this. I showed you this in the earlier session, but in medicine, in advanced materials, solar cells, agriculture, consumer products, commodity powders, you'll hear a little about it. You give me a time because Samuel has to talk. So there are important topics, right? Where does the fundamental knowledge again come in? Condensation, you already heard. I'll just mention nucleation. Remember now, I want to make these particles. What is the best way to make it? I don't take a big piece of gold and start hammering it. It'll take me forever, and I may never get down to that small size. Instead, I will start with a molecule and try to put these molecules together. So our reactors, which you'll see tomorrow or during the tour, instruments, right? We want to measure these as we are making it. So the molecules can be assembled together and brought together to prepare particles of a known size. We obviously do this for a certain function, and we have to characterize them, then also measure the functionality and so forth. So this process of going from individual molecules to a stable cluster or a particle, in this case, nanoparticle, we can in general refer to as nucleation. I will just talk about a classical nucleation theory, though I must say that it really breaks down for many of these processes that I just talked about. But, we have to start with that. And being a tutorial, we'll just talk about that. So there is a concept of a critical size. So, and this literally is where did these particles come from? It happens in the atmosphere. It happens in our reactors and so forth. So simple thermodynamics, right? We know the concept of free energy change. there is an initial free energy of the system. Initially, they are all molecules. We can, as I said in the earlier tutorial, we can call that a vapor. And then we have some of these clustering to create a nanoparticle. And we also have remaining vapor. Not everything clusters together, right? So we can call the new particle an embryo and remaining vapor. So it's the free energy change. And then I can write this equation for the free energy change based on the specific free energy. So you can see that the initial system, there are n sub t molecules. And for each molecule, the specific free energy is G sub V. It's a vapor, right? And that's the initial. And the initial, the first terms are for the final system. Some of them have clustered. G molecules have come together, and NT minus G remain in the vapor state, but G of them form a liquid. We'll call it a liquid or a cluster. It's G times G of them times G sub L, right? Then there is the surface energy. It takes some effort to bring them and they stick together. It's because of the surface energy. We'll just use a surface tension term. I mean, a question was raised about that. What is the surface tension expression? Those are more advanced questions, but let's just look at it at a high level. Then I do some simple manipulations. Always good to little more math. Look at ideal gas law expressions, and you can go through the analysis. You will get a ratio of the partial pressures, and then the saturation state. And there is something known as the saturation ratio that was also mentioned in the earlier talk. But let's look at a graph. I'll take this free energy change and plot it as a function of cluster size. And you see it's a inverse U-shaped curve. Normally in a chemical process, when we reach equilibrium, delta G becomes a minimum. Here, delta G reaches a maximum value. And this is known as a metastable state, right? So nucleation is a metastable process. If the conditions are right, I'm going to form a stable cluster, and then these clusters will grow. If the conditions are not right, the clusters, it might cluster, but then it'll just evaporate or break up again, right? So very interesting. And this is a metastable process. It's a sort of an equilibrium. We have to cross this equilibrium state, and that size we refer to as the critical size. So this is the smallest size of particles that I can form in my system. Of course, if I'm engineering a reactor, I want to change these parameters. I want to change the temperature, pressure, saturation ratio, which is concentration, and try to change the size. And then, of course, we have all these growth mechanisms. So very straightforward, okay, in some sense, some detailed, but you can work this out. You can calculate this critical size, and you can use it to design, even in a very simple manner, your aerosol reactors and so forth, right? So and you can also see how the cluster size numbers change. If the saturation ratio is greater than 1, you can see the clusters of larger size increase. If saturation ratio is less than 1, they'll just evaporate out and break up again. Okay, so, and of course, that minimum point is the critical size that I referred to. Okay, so these concepts allow us to now design reactors. You can do calculations for water because it happens in the atmosphere, right? Same things happen. If the saturation ratio is low, I need a much more larger cluster for it to be stable. If the saturation ratio is high, the cluster size reduces, so I can more readily form these particles and so forth. Okay, so, and we can have it in a reactor, we can design it and so forth. There's the rate also. Ultimately, I am an engineer, I want to produce these, I want to make them, I want to go sell them, or I want to design an application. So the rate becomes important. We can also derive a rate expression because I don't want to wait forever to create these particles. In fact, the rate is extremely fast. And that's the beauty. That's why industries that make these, they love these gas phase processes. Very quickly, they could produce it in very large reactors, large quantities, and so forth, okay? And this is the rate expression, lot of terms. It's a longish expression, but I'll let you, of course, see it if you want to get into more detail. They are in our notes, and you can follow this and so forth. And we can then calculate the rate. I'm going to skip this condensation. In fact, some of the slides will look similar. And what do we do all of this? So you heard about condensation, you heard nucleation. I was talking about transport. You heard a little about diffusion. We didn't talk about collisional growth or coagulation. So we put all these terms together and we get what is known as the general dynamic equation. It looks extremely complex, but we have very detailed computer codes to solve this. Sometimes it takes a lot of time. There are different approaches. We can use sectional models. You heard about the sections that we defined. To be very precise, I want to track every particle size. So those are discrete models. It'll take forever. Even the best supercomputer that we have on our campus is going to run out of horsepower. So we will combine discrete with sectional codes. There are machine learning methods that are used, which are data-based approaches, and a lot of exciting work going on. And we put these together, make them available, like even in GitHub accounts, so others can use it. But going back, an application engineer or a scientist will use these for their specific problem of study. So the change in the size distribution function, that is important because that's what we are after, is impacted by transport terms, by movement terms, by collisional growth. And of course, if I'm starting with a pure vapor, I also have nucleation and so forth, right? And some terms will drop out under certain conditions, so we can look at that. So in the remainder, let me skip this, right? It allows us to produce these particles in a very controlled manner. I can control the size by solving that equation. I design a reactor. I might want to control the shape, definitely the composition, not only the composition, the chemical composition, the structure. I might want to deposit into a thin film. And of course, as I do this, I want to have online measurements, which you heard of. I want to use my models so I succeed, right? So there are all kinds of particles that we can produce, and some are very pretty. Of course, electron microscopes are used to image them and so forth. Okay, how do I make them? And this is just a few reactors from our lab. I see Dibyendu came in. He's setting up his lab with even more fancier plasma reactors combination. But this is a simple flame reactor. Remember, I want to get molecules, right? Because that's my starting system. How do I change something into molecules? I can take a bucket of water. That's a whole bunch of molecules. How do I do it? I want to evaporate it. How do you evaporate something? Heat it up. I want to do it quick, so I want to use high temperatures. I also like high temperature systems because I can react two chemicals to make a third chemical, right? I might want to make silicon oxide, very pure for an optical fiber. I might want to start with silicon tetrachloride, react it with oxygen. So flame reactors are extremely common. And if you go into a lab, you'll see some of these going. And the top part is all components used to pull the particles out and collect them, because here we really want to collect them and then use them for different applications. And these are, I show you a simple picture, but there's so many components, knobs to turn, gases to bring in, reactants to bring in. So the control systems are quite involved. And the burner itself has a certain design depending on the application. And then, of course, the collection system. And I can also use a furnace. I don't need to use a flame. I can use external heat to heat up my reactants to go into a molecular state, form particles. Sometimes I don't go all the way to the molecular state. I might just decompose a precursor. That's okay too, right? So a furnace allows me to do that. It looks something like that. And then there are certain things like electrospray systems. I use a spray to feed my precursor, but I place a charge and I produce very uniform droplets. And these are different control stages of the electrospray that I can alter and produce different types of particles and so forth, right? I saw Wu Jin come in, he's somewhere here, I think. This is from his work. He designed this system to not only produce particles, but to actually deposit it. And we called it a aerosol CVD system, aerosol chemical vapor deposition system, right? And here, again, I'll skip all the different conditions. You can get different types of deposits. And if these are electronic materials, I want single crystal, very high conductivity kind of deposits, and the middle part gives me that. If it's for chemical reactions, a catalyst, I want very high surface area. And sometimes I want a very dense film. So in a simple system, by tweaking the processing parameters, we can get different kinds of deposits and films and so forth. Okay, where do we use this? I think very quickly, I have a few more minutes. 2 minutes, okay. What is the problem we face today? We talk about climate change. The sea level is rising. We want our Rosenstiel campus to be above sea level. You know, CO2 is causing problems, but we need to solve this. Nanotechnology can help. It can actually pick up the CO2 from the air and convert it to something useful, right? So it helps remove it. People are designing systems to do that because we are getting desperate. We have to tackle it. I could also reduce emissions by controlling the CO2 at the source. I'm just talking about catalytic systems, very well designed, that can be used to take CO2 and make it into a useful material, right? And a lot of these projects are going on, very challenging, not easy to convert CO2. It's a very stable compound, but we have to reduce it. Then we have to react it to make value-added materials. Because if I really just want to trap CO2 and do something with it or bury it or store it, that's not very good. I want to close the cycle, you know, concepts of circular economy and so forth come in. So nanotechnology will make it happen. This is another example using graphene and a TiO2 nanoparticle to promote this conversion. And these are different structures. We are also using graphene to deliver drugs to treat cancer. When you have cancer today, you take a chemotherapeutic, it goes all over our body, you have side reactions, and it's very problematic. But if I could design a nanoparticle which only goes to the tumor and destroys it, that would be great. So we are working with a school of medicine to design these kinds of drug nanoparticles and so forth. So whole bunch of nanoparticles made in our lab, used for solar energy, drug delivery, CO2 reduction, name it. It is so exciting. You choose your application, and maybe you could design a process to produce a material with an aerosol reactor, okay? So these are actual projects. I'll go through it. I'll pause here. I'm going to turn over to my colleague. He'll tell you even more exciting things, maybe even more routine applications, but fascinating applications. So we'll change this. Mm-hmm.
Can I just change, can I use this or to
Yes,
change slides?
yes.
But I have to stand in front of this for the thing, right?
Yeah, you can try
Okay,
the
okay.
clicker.
Okay. All right. Thank you so much again, Dean Vishwas, for kind of the great introduction to nanotech.
So as Dean Bishwas mentioned, nanotech is everywhere. It's ubiquitous, right? So I'll kind of give you a kind of a quick overview of some of the applications that kind of I've actually faced, and I work with on a daily basis with a lot of industrial partners. So if you look at kind of nanotech, and there's various kind of versions of it, in the sense of people talk about nanomaterials, nanotech, and then also soft matter, but at the end of it, it is on a nano scale, that you're kind of utilizing materials, and you're sometimes using self-assembled materials, or you're utilizing materials which you've synthesized, as you just heard before, and you incorporate them into various products. So most of the world of cosmetic and consumer products, and also kind of pharma and foods and agricultural products, spans a wide range of nanotechnological innovations, right? So it kind of goes from kind of self-assembled systems to kind of systems where I would say are composites in the sense that you have polymers with particles embedded in them, to kind of systems which are kind of smart and responsive as well to external stimuli, right? So kind of pH, temperature, all of these aspects. So I tend to move around, and I know to stand here for the thing. So yeah, so that's kind of important to understand that in real terms, some of these applications which seem very very day-to-day applications, whether you're kind of painting your room, or you're kind of brushing your teeth, or you're applying kind of a shampoo, seems like they're very simple kind of applications, but there's a lot of engineering and nanotech which goes into even these simple products and simple applications. And a lot of it is based on really understanding the kind of fundamental basis of what actually gives the performance. So one thing to kind of understand is that when you look at the back of a shampoo, or you look at the back of a consumer products, you'll see 15, 16 ingredients. But the reality is that the functional performance is actually controlled only by a few of those. And those are the ones which is kind of based on, I would say, like nanotechnology principles, where you're kind of actually engineering a lot of the microstructure and properties to give you the final performance benefits that you look at, right? So, I mean, although we kind of are going to kind of skim through some of these, I'm not going to go into a lot of the polymer aspects or the hydrogel aspects. I'm going to focus in on nanomaterials and nanoparticles, because that's kind of the theme of this workshop. So I'll talk to a little bit about some of the applications of nanoparticles and particles within the context of consumer products. So I'll talk a little bit about sunscreens and photoprotection, where you'll see the application of nanoparticles. We'll talk about antiperspirants and deodorants. I'll talk a lot about kind of film formers, and people don't realize that actually particles are utilized very extensively throughout the consumer world to form films. And film formation is almost a very critical kind of criteria of the performance of lots of different consumer products. And we'll talk a little bit about that. The other one, which is kind of getting a much more higher kind of priority in terms of R&D spending, is active delivery, and kind of looking at delivery vehicles. So this is where the world of biotech and kind of pharmaceuticals is kind of starting to intertwine with consumer world, because if you look at even cosmetic and consumer products, the way innovation is going to come through is primarily to bring about biological changes. So it's not going to be purely based on cosmetic changes, or I'm just going to get an optical effect, or I'm going to get some sort of a texture effect on my skin, but actually changing kind of the kind of actually causing skin regeneration and causing biological changes. So most of the cosmetic companies are now kind of designing delivery mechanisms or delivery vehicles where they can deliver various bioactives, which will kind of cause a regeneration of the skin. So this is all the anti-aging movement which is going on in the consumer world. So we'll talk a little bit about that. Lots of consumer products, also pharmaceuticals, also foods, are emulsions, right? Because you want to bring in actives, which are, some of them are soluble in the oil phase, some of them are soluble in the aqueous phase. But you want to kind of deliver all of that in a product. So you have to kind of deliver that through emulsions. And particle stabilized emulsions or Pickering emulsions are, again, something which is gaining a lot of popularity in the external world. So in all of these cases, you'll see a lot of aspects about utilizing particles and kind of to generate new, performance benefits. So why all of this change in kind of this industry, right? Because you might think that toothpaste and shampoos and body washes and all of these skin lotions, these have been around for so many years that there's probably not a lot of innovation which is going on, and what's so new about this industry, right? So there are changes in the market and there's changes in regulatory environments, which are causing kind of these industries to start to rethink and re-engineer all of their formulations. So what's happening is there's some drivers which have come into the market. One is obviously sustainability, because if you look at kind of market drivers and you look across cosmetic and consumer products, and you look across kind of your kind of whether it's cosmetics or your shampoos or body washes or your foundations and lipsticks, all the way through to kind of even paints, inks, and coatings. Everywhere there's a kind of a strong driver for biodegradability of your ingredients and sustainability. So for companies which have been kind of making these products for lots of years, they have to now rethink the entire formulation design so that they start to bring in novel materials, but still maintain the performance, right? So you can have the most sustainable green shampoo on earth, but if it doesn't foam up, if it doesn't clean your hair, if it doesn't remove dirt, if it doesn't build up the rheology or texture, no one's going to buy that shampoo in the next day, right? So the reality is that you have to focus on novel materials for sustainability, but at the same time, you need to be able to engineer the performance back. So that's from the market perspective, where the market and the consumer is demanding kind of more green formulations, but there's also regulatory environments which have come in, right? So so especially with particles, microparticles and nanoparticles, which have been utilized in the industry for a long time. And I'll show you some of the examples, but there's been lots of strong regulatory changes which has come into play, especially in Europe, which is now preventing kind of a lot of these companies from doing business as usual. You need to kind of rethink about, okay, how do I still get some of these benefits, but how do I start to generate new sustainable particles or biodegradable particles, which can still give us the performance benefits. So this is important to understand, that it's this dual driver of market and consumers, as well as regulatory changes, which are driving lots of innovation in R&D across the consumer industry, but not only consumer. As I said, agricultural products, food products, paints, inks, and coatings. Every day, I get inquiries from industrial partners asking me to reformulate a lot of different formulations. I'll just give you a couple of examples. I think last week I had a call with Bic Pens, you know, the pen company, which you're always writing with things. And they wanted me to ask me that, okay, can we re-engineer our ink formulation so it becomes more sustainable, but you still kind of get the same quality of writing, right? So it's a very simple example, but it's one of the things where they need to re-engineer their formulation. There's aspects about kind of in shampoos and body washes everywhere where people are asking a re-engineering of their formulation. So it's important to understand that there's these market drivers which are changing the industry, which is causing this industry to invest very heavily in R&D right now. So as I was giving a conference talk at the World Surfactant Congress, and in one of the panel discussions, I said that for this industry, we're kind of reaching an inflection point. This is the point where kind of industry has to re-engineer and kind of rethink about formulation design completely, and think of it in a holistic manner in terms of how do you kind of bring the entirety of the formulation together, but not only in terms of the formulation design. We have to take into account the processing and the manufacturing of these products. How do you minimize CO2 production, right? So how do you bring in carbon capture? How do you start to bring in the entirety of the life cycle of these products and kind of make sure that you're kind of doing this in an environmentally sustainable way, right? So these are a lot of these drivers. So here, a lot of the things that what you have to entail when you're re-engineering and reformulating is you have to re-establish the microstructure property performance linkages all over again, because you're now starting to re-engineer with new materials. And you have to understand that these systems are complex. You have interactions between particles, and you have interactions between particles and surfactants. You have a lot of self-assembly going on in these systems. So how do you engineer that complex system to give you that performance benefit? And it's not only kind of your formulation which impacts structure. A lot of these systems are also metastable. So the reality is that processing kind of can put you into a into an local energy minima, and you kind of live there from that perspective. And that has a lot of implications in terms of your performance benefit. So kind of the thermodynamics of some of these processing aspects is very important as well. So in general, I'm going to leave out the whole aspect about self-assembled system, which plays a very important role, and I'm going to leave out interaction effects and all of that, which is very important. So if you're interested, we have a couple of workshops coming up. One is on kind of understanding rheology control and particle sizing and in liquid formulations or complex formulations, nanoparticle tracking. So we have a full workshop on that coming up in February, end of February. So if you're interested in that side of things, do come to that. If you're interested more in kind of cosmetic and consumer products, we have another workshop coming up in March, which is focused on a lot of that and some of the newer tools and techniques utilizing kind of high throughput automation and machine learning and AI as well. So some of those things are coming up, but if I just kind of focus on nanoparticles and kind of their applications in cosmetic and consumer products, it's almost the same parameters you just heard about for the rest of the afternoon. It's particle size, it's particle size distribution, it's about stability. So you don't, and one of the challenges is when you put these particles into complex formulations where you have kind of hydrophobic moieties and you have high kind of screening of electrostatic charges through salt addition, differences in pH conditions, you start to make these unstable. And you start to agglomerate or aggregate these particles, and that becomes a challenge. And then basically also the aspect of rheology is very important because these particles, depending on the volume fraction you're using, can start to play a significant role in building the rheological system of this as well. So I'm going to skip through a little bit faster on the characterization aspects. As I said, we have a full kind of workshop coming up on these sort of characterization techniques at the end of February. So, I mean, if you're interested, do get in touch with me for that. But one of the things that we tend to do a lot is also particle sizing of the particles that we utilize in cosmetic and consumer products. One of the techniques which is used quite extensively in the cosmetic industry and consumer industry is dynamic light scattering. Again, it's a non-invasive technique. You're just following the Brownian motion of particles, and you're kind of getting the translation and diffusion coefficient. And from the translation diffusion coefficient, you just apply the Stokes-Einstein relationship, and you get out your size, your diameter of the particle. Some of the challenges here is that primarily that when you are in formulations, there are other aspects which are at play here as well. And it's not as simple as just putting particles in a purely kind of a DI water solution and measuring it, right? So you are actually trying to measure it. And this is where the challenge comes in as close to real formulation conditions as possible and understanding what's going on. So there are developments in light scattering, which have helped us to start to move in that direction. I'll kind of highlight a little bit of it. But remember that one of the challenges which happens is that not all particles are spherical. And when you start to kind of use a spherical form factor to fit kind of your scattering intensity, you end up with errors, right? So and that's a thing to kind of keep in mind. But so it's just that, I mean, it is still used. People tend to dilute their formulations and kind of just apply kind of dynamic light scattering. And as you know, it's a very simple technique. You kind of put your sample in a cuvette, you're kind of shining a laser light on it and kind of you're kind of collecting the intensity fluctuations. And from the intensity fluctuation, you kind of construct a correlation function, which is kind of looking at the correlation between scatterers at a time t and t plus tau. And from there, you get your kind of correlation function or your intensity correlation function, from which you can also get the electric field autocorrelation function. But the main aspect of it is you kind of get your autocorrelation function, and from there, you start to extract out both your particle size and particle size distribution from that perspective. The other area which I was saying was important to characterize is the charge interactions. So we kind of tend to use electrophoretic light scattering to kind of get zeta potential measurements. And again, here it's one of the things which is important in cosmetic and consumer products or ag products or any other of these formulated products is stability. Stability not only of particles, but a lot of sometimes these are in emulsion format. So trying to understand droplet stability and kind of emulsion stability becomes very important. And building charge repulsion into the system is one of the ways we kind of tend to stabilize a lot of the formulations. So because obviously there's lots of attractive van der Waals interactions, and you try to kind of charge stabilize, kind of building in kind of this this double layer repulsive interactions into the system. And so, and you need to be able to overcome your attractive van der Waals with your repulsive interactions. And that's kind of the general method a lot of these industries have employed. And so they tend to measure zeta potential, which is again the potential at the diffuse layer. And I'm not going to again spend a lot of time on this. I'm going to spend a little bit more time on the applications, but just to show that you're kind of measuring the potential at this diffuse layer of the ions. And you do that again through this electrophoretic light scattering. So primarily you have you put your kind of sample in a cuvette, but the difference with this cuvette is that you have electrodes or two ends of it, and you apply an electric field, and then you're looking at kind of measuring the electrophoretic mobility as the particles are moving due to this electric charge that you've applied. And primarily, it's the same principle. So you kind of are using light scattering principles in which the light which is scattered off, you're measuring the intensity fluctuations, but this time it's the intensity fluctuations due to the motion of the particles due to the application of the electric field that you've applied, right? So that's kind of the way you start to extract out zeta potential. And in the world of consumer, cosmetic, ag, pharma products, people have come to rules of thumb, if you will, that kind of having kind of high charge repulsion means kind of values of negative or positive 20 millivolts and above. And if you kind of have built in that amount of charge repulsion into the system, you tend to end up with stable systems. But then they tend to change pH and things change, and life becomes more difficult. But anyways, this is one of the methods that is used for characterizing these sort of systems. And the third is rheology as well, which I'm again not going to go into. We can kind of talk a lot about it in the workshop in February if you're interested. But again, rheology plays a very significant role in lots of these products. So for example, you've all kind of heard of monoclonal antibodies, which are all these biotherapeutic drugs. And if you look at most of the big pharma, they're all kind of changing from small molecule drugs to these protein-based therapeutics. And again, these protein-based therapeutics are kind of particles which are a couple of nanometer in diameter, but the reality is that they're very susceptible to aggregation. And one of the problems with that aggregation is that the viscosity starts shooting up. And if you look at where the biopharmaceutical industry wants to go, they want to make these drugs all self-injectable. So it's like insulin, right? If you look at insulin, people take it out of the fridge and they self-inject it. But you want to have that same sort of ease of use for things for oncology, for anti-cancer drugs, for rheumatoid arthritis, for kind of even asthma. So most of the drugs which are coming into the pipeline are all liquid-based protein therapeutics. And high viscosity is a big challenge for them. So we just got funding from a major biopharmaceutical company to address this problem of high viscosity. But again, if you look at particles, it's the same kind of usual suspects, which play a role in rheological kind of performance aspects. So it's about volume fraction of the particles. It is about the particle size distribution, electrostatic interactions, shape, molecular weight, right? So these same sort of aspects of it. Again, I'm not going to go into rheology, but I mean, there's traditional mechanical rheology, which you kind of put your sample between two plates and you apply a kind of a known force and you're measuring the response of the fluid. And from there, you can construct a kind of you can get back your elastic modulus, or you can get back your viscous modulus or your viscosity. But there are advances in techniques as well. So people are starting to use a lot of kind of optical microrheological techniques. Here again, we kind of look at probing kind of probe particle motion in complex fluids. So if you put probe particles, and these are nanometer scale particles, and you put them into a Newtonian fluid, right? They're kind of the motion is very different than when you put these probe particles into a viscoelastic medium, like a polymeric system. The motion is very different, right? And so what we've done is basically, you can kind of start to extract out kind of the mechanical response of the fluid from the motion of the particles. So from the mean square displacement of the particles. So again, there's a couple of techniques. I actually have granted patents in this space as well. And there's also a lot of kind of publications in this space as well. But you can then extract out a lot of the rheological. Is very similar. You kind of look at your kind of intensity correlation function, and you extract out the mean square displacement of the particle. And from this mean square displacement of the particle, you can then start to extract out a lot of changes in the dynamics of the systems as systems start to self-assemble, and a lot of other aspects of it as well. So again, not going to go into details here, but I just wanted to give you a flavor that even in rheology, there's a lot of new innovations which have come into play, which allows us to probe very sensitive systems and allows us to look at very small materials. If you're looking at biotherapeutics, for example, you cannot use a rheometer because they'll just give you 500 microliter of sample to play with. It's impossible to use a mechanical rheometry. You have to use these novel techniques. And these techniques can be utilized for other things. I'll give you another example. Just looking at mean square displacement, you can start to extract out kind of a stability of emulsion systems. And you can detect not only emulsion systems, but also particulate systems. So what's very important is that in the consumer world, the way they look at stability is they'll kind of take a formulation and they'll put it at 45 degrees and wait 6 months and see if it's becoming unstable. But what if we could do that stability test in a couple of hours? And that's what we've done in one of these measurement techniques I'll show you at the end, where we've just published that a little while ago, where we kind of showed that actually you can use diffusing wave spectroscopy to actually be a very sensitive measure of stability in particulate and emulsion systems. So I know I'm kind of spending a lot of time on characterization, but I just wanted to show that it's important to understand and characterize effectively. And for the complexities of these formulations, you need sometimes advanced techniques to look at them. And that's the main takeaway message. And those advanced techniques are giving us a lot of new insights. But just very quickly in the next 5 minutes or 6 minutes, let me just kind of highlight each of these applications. So one of them is sunscreens. So like if you look at sunscreens, there's two kind of, I would say like sunscreen actives, which are utilized. There's chemical sunscreens and there's physical sunscreens. So physical sunscreens are basically your TiO2 and zinc oxide. And these can range from nanometer or to micrometer scale sizes. And primarily the principle is just scattering, right? So that you kind of have a layer of particles and you kind of, with their size range that you are forming on the arms or wherever you're applying it, they scatter off the particles in the right UV range of wavelength, right? And therefore you kind of get protection, sun protection from that. But with chemical sunscreens, pretty much what happens is that they actually kind of allow the UV rays to hit the skin, but transform it into these non-damaging wavelengths of light or heat. And there's a range of these, what is it called, chemical sunscreens, which are available. But one of the things is that because they penetrate into the skin, there's a lot of regulatory changes which are coming into place, which are preventing the use of these chemical sunscreens. And if you look at one of the US states, which was first to ban a lot of these ones, is Hawaii, because they kind of looked at not only the medical kind of implications of it, but they kind of also started to look at environmental effects of utilizing these chemical sunscreens. So these nanoparticle-based TiO2 and zinc oxide-based particles are still, I would say, more favorite of the FDA than these chemical sunscreens, although they're nanoparticles and they have aversion to that word, but they still kind of are more supportive of these sort of nanoparticles for sunscreen applications. The challenge with sunscreen applications is because of the size range of particles that are used, and the scattering that we want to achieve, they tend to give this white kind of tinge on the skin surface, and people don't like that, right? So the challenge for cosmetic companies is how do you get that adequate sunscreen protection, but at the same time not have this white kind of mask on your face or on your body, right? So that means kind of what they tend to do is start to play around with the particle size and then kind of get like a distribution which starts to give enough protection, but also kind of tune down the white hue, if you will, from that perspective. So that's what they tend to do. But usually what they'll do, because they still don't get adequate UVA, UVB, and UVC coverage, they'll usually mix nanoparticles with some chemical sunscreens. And that's usually the product formulations you'll still see on the market. But there's always innovations which are going on in terms of creating new nanoparticles, which will give adequate sunscreen protection and have the right scattering profile and biodegradability and environmental profile. So that's an important aspect to keep in mind from the perspective of sunscreen. The only caveat there is that you have to, sunscreen is classified as an OTC product, which means that it's not a cosmetic, it's not a drug, but you need to kind of classify it as a drug for selling in pharmaceuticals or if selling it in other aspects. So what that means from a FDA perspective, you have to follow the FDA monograph on sunscreens. So you have to follow exactly that formulation. And if you want to include a new sunscreen active, you have to go through the FDA regulatory approval process, which is people tend to stay away from that to an extent. So the next one is antiperspirants. Here again, people tend to use, just to highlight this, a difference between an antiperspirant and a deodorant. A deodorant just masks the odor, right? So again, we don't want to go into that detail, but obviously when we're sweating, we have an odor, and basically deodorants are just scents or fragrances which mask that. But antiperspirants actually stop you sweating, right? So what it does is you have nanoparticles, and these are aluminum-based nanoparticles, which are introduced into the formulation. And what they tend to do is they penetrate the sweat gland duct, and then they start to gel up inside that duct. And so what it forms is a gel plug inside there, which prevents sweat from coming out. And so it's a very smart sol gel process, which is actually kind of instigated. You need the right particle size for it to enter into the sweat glands. But then once it's there, kind of the pH, which is there, triggers kind of a change from sol to gel and plugs it up. And that plug stays for several days from that perspective before you need to kind of apply it again, right? So this is, again, an interesting application of nanoparticles, which are kind of utilized to kind of undergo a change in your physiology, if you will, and plug up your sweat glands so that you kind of don't, then you stop sweating. Obviously, antiperspirants can be delivered both in terms of sticks or gels or deodorants, right? So again, deodorants in terms of aerosols as well. So this is, I just wanted to put it in because this is an aerosol conference. So again, kind of talking about that you can deliver some of these through aerosols. Again, deodorant aerosols are very simple because you're just kind of delivering fragrance. That's all you're doing. Antiperspirants are more complex because here you have to deliver the nanoparticles, and you have to deliver it again so that with the right size range, and you need to make sure that the nanoparticles maintain their size range in the aerosol formulation and don't get aggregated in there, right? Because again, you need that for transport and kind of aerosolization in the right size range so that it can penetrate into the sweat glands and then cause the plugging of the sweat glands, right? Active delivery is very important, right? And again, I've given you a range of different types of active delivery systems, right? So these can be liposomes, polymeric nanocapsules, nanostructured lipid carriers, solid nanoparticles, nanoemulsions, obviously micelles, hydrogels, and scaffolding, right? Again, so one of the things which is a kind of a strong driver in the industry is primarily kind of causing skin regeneration, right? How do you reverse anti-aging, or how do you reverse aging? How do you create really efficacious anti-aging products, right? And almost all that, this is like the holy grail for a lot of the cosmetic industry. But in order to achieve that, they understand that just kind of providing anti-wrinkling effects through kind of optical or texture effects on the skin is not going to cut it, because consumers are aware that, okay, this is just a temporary fix. I want something which will actually regenerate my skin. So then people are starting to look at these kind of epidermal growth factors, which start to actually penetrate into the skin and then you start to see a regeneration of a lot of the proteins and the skin cells, the fibroblasts and keratinocytes, which make up a lot of our skin in the dermis layers, right? So you want to see a regeneration of that. And there's mechanisms of how these kind of epidermal growth factors upregulate kind of some of the biomarkers which control kind of this skin regeneration. The challenge is, how do you deliver these through a formulation, and how do you deliver it through your stratum corneum or your upper layer of the skin? So the upper layer, a layer of the skin is a very protective layer. And it's protective for a reason, right? It does not want kind of a lot of external particles or external viruses or other things to penetrate into your skin, right? So it's actually quite challenging to be able to make delivery vehicles which effectively pass through the stratum corneum. You have to play a very, and the stratum corneum is made up of a lipid structure. And so you have to kind of almost fool or kind of trick the stratum corneum to believe that this is something of the skin, right? So you have to create lipid structures which have the right hydrophobicity and has the right charge density to allow penetration into the skin. And so there's a lot of research and R&D, which our group, again, is one group where again, we just got some funding from a company to generate, and our postdoc just joined us, and he'll be working on developing some of these kind of hydrogel-based delivery mechanisms for cosmetic companies. But again, here the size is very important, but also the chemical characteristics is very important. I think we're done. I'm going to finish here. So the last thing here is film formers. As I said, again, a lot of these film formers, they can be delivered if you can, nowadays they can be done through sprays, but they're also kind of delivered when you're kind of applying a product. These are particulate-based, nanoparticulate-based film formers. And if you look at the process, again, you kind of see, if you're taking a cosmetic products, it's an aqueous-based system, the water tends to evaporate, the particles come closer together, and you start to form one kind of continuous film. And that film property is very important, because if you look at cosmetic products where you have, or even hair care products, optical property changes on the skin are very important. So if sometimes what happens is you'll put in certain actives with certain, and again, another set of nanoparticles, which will give some level of kind of scattering, which will make your hair look shiny, for example, or will start to give a certain glow to your face. So you're starting to generate optical effects on the skin, on the hair, and other effects. And you do that through a combination of kind of forming a continuous film with nanoparticles embedded within it as well. So the particle formation itself is from particles or nanoparticles or microparticles, but then you have within that embedded other sets of nanoparticles. But again, the film formation, the rigidity of the film plays a very important role in terms of application. So if you look at pigments or sunscreens, how do you ensure proper distribution of the pigments? How do you ensure proper distribution of the sunscreen? You don't want sunscreen actives like TO2 to be clustered in one area and not be present at all in somewhere else. Or for paints, it needs to be, the pigments need to be uniformly distributed. Having a film where you have that distributed effectively is very important and critical. And the last one, as I said, is primarily particle stabilized emulsions, right? So again, usually emulsions have been stabilized by surfactant systems, which are amphiphilic molecules. But nowadays, people are starting to move towards Pickering emulsions because they see that you can tend to create much more stable emulsions. And that's primarily because these particles, which are again, hopefully they're kind of more also biodegradable, but these particles tend to cluster very tightly at the oil-water interface. And what that does, it creates a very strong interfacial elastic layer at that interface, which is not possible to get with surfactant systems. And that strong interfacial layer makes it look like a bouncy ball, like a rubber ball, right? So basically, if it's so elastic, when it comes together, it's not going to coalesce. It's going to bounce off each other. And therefore, you get much more longer-term stability than you would ever get from a surfactant system. So the possibilities of nanotech and nanoparticles are endless. So from the perspective of where the world is going, I think there's a lot of kind of scope for innovation in terms of the nanoparticle types, the chemistries, the shapes, the sizes. And incorporating them into lots of different formulated products, I think, is going to create a world of different opportunities. And hey, there's a lot of R&D funding available. So let me end it there, and hopefully I gave you a flavor of a very different world and the applications in that world. Thank you. Any questions? On the one in the chat, how do I check that? Oh, okay, now I can see it. All right, you can move. Okay. So yeah, there's kind of, you know how this works. So the question was, how do states government decide which chemicals to ban and which ones to allow in consumer products? Is this decided scientifically or more through lobbying? So this is interesting because I was actually invited to an EPA closed workshop a couple of months ago. And I was the only outside person, and there was like about 30 or 40 people from the EPA. And what they wanted to understand was consumer products and formulation, because they're starting to kind of create a lot of regulatory kind of changes, and they're not fully aware of what happens when you have complex formulations, how interactions and other effects start to impact on toxicological profiles. So there is an aspect of, I think, trying to understand scientifically from that perspective. I think it's complex. There's an aspect of lobbying, obviously, but there's a lobbying on both sides. So in the sense of the chemical, the cosmetic and consumer companies also have strong lobby lobbyists, as well as chemical companies. So I would say it's kind of driven a lot by lobbying, but at the same time, it's not like that the EPA and FDA is completely ambivalent to kind of understanding what is going on scientifically. And they're trying to make efforts to try to understand things more scientifically, because one of the things, and again, I can't highlight all of them due to confidentiality, but one of the things is just like they were doing tests on paraben levels in human beings, and they kind of got it from urine samples. And it was interesting to see how the exposure levels of parabens is so high coming from various different chemicals, and you don't even realize it, right? So kind of understanding how these things actually translate across multiple products, because, you know, like, for example, parabens were utilized not only in one product, in the daily routine that Pratim highlighted. When you get up in the morning and you're shampooing, you're using a toothpaste, using kind of other deodorants, right? Your parabens in the previous times were utilized in a lot of those products, even on textile aerosol sprays, right? So when you're using Febreze, right, and you're kind of doing fragrances on your textiles, and you're sitting and watching TV, you are inhaling and you're kind of taking parabens into your system. So the EPA workshop, which I was there for like 3 days, was really trying to figure out what are the different exposure routes of something like paraben, and what are the different kind of formulations which can bring about a cumulative effect. So what that means is that in the future, if they kind of understand this cumulative effect, the regulations will be much tighter, because you will start to see that there's a cumulative effect from multiple different products which are building up. So the amount of concentration you can have in one single product needs to be much better controlled. But anyway, that's a long-winded question, long-winded answer to these questions, but it's a complex area. So I think it's something where people are starting to kind of look into much more carefully. And I think especially with new regulations and environmental directions, people are going to start to rethink a lot of this aspect. Okay. Yeah.
So you mentioned that you got a grant to look into, I guess expanding more on the injectable medication. And one of the problems that you're dealing with is the high viscosity of the
Right.
plan to work deal with that viscosity. I know it's a newer field.
Yeah, so primarily Oh, yeah, so the question here was that, I mean, one of the projects that we've just gotten a grant for with a biopharma company is focused around kind of managing viscosity, kind of enhancement in these formulations. So how do we kind of tend to address that and manage that? So that was the question. So the reality is that lot of these protein therapeutics, they actually are quite good at low concentrations. So one of the things is that if you kind of now have rheumatoid arthritis, or you're kind of going in for treatment for anti-cancer, and you're using some of these chemotherapeutics, you tend to go into your doctor's office and take an IV drip, which is usually delivered at low concentrations. And there, your stability of the particles is quite good. Because it's just very low concentration, you're just delivering it at much higher volumes. But that takes it can take several hours. It's inconvenient, right? Basically, you have to go into a doctor's office every week and sit and take an IV kind of drip for several hours. So where the biopharmaceutical industry is investing a lot of money is how can we kind of take these drugs to high concentrations, so that we can have self-injectables, just a small amount of it at high concentration, but then only take that once a week, or kind of, or maybe once in 2 weeks, right? But what happens is that you go to these very high concentrations, the interactions get magnified. And the reality is you have a lot of charge interactions in the systems. You have a lot of hydrophobic interactions in the system. It's a matter of trying to, how do you kind of bring in other formulation aspects to manage those interactions, right? How do you start to kind of, first of all, understand what those interactions are, right? So a lot of it is about going back to thermodynamics and understanding those interaction effects, and then trying to see what are the control parameters I have in order to kind of optimize that. The other routes to do that is, can I use a delivery vehicle to deliver that instead of having it in the formulation? Can I kind of incorporate it into a nanoparticle or nano carrier or some sort of nano vehicle and deliver it? And there it's easy. You don't have to deliver it through the skin. You can inject it. So I think that delivery is good, but you just need to maintain the efficacy and the entity or the drug efficacy of the therapeutic, these monoclonal antibodies. You have to maintain that in that vehicle, right? And so and make sure that it's released at your drug target, right? So that's one of the things. It's all of this. It's all kind of comes back to the same aspect of kind of utilizing kind of soft matter and nanotechnology to solve a lot of these problems. And a lot of the problems are the basis of them is very similar. And and one of the things is to take the learning from one industry and apply it to another, right? Just 1 second to kind of finish on that is that if you look at the food industry uses protein self-assembly to structure foods and actually give you texture so that you like that. But the biotherapeutic industry wants to avoid any aggregation and self-assembly. So kind of learnings from one industry can actually be applied to another industry. And that cross-industry learning is where innovation takes place. And a couple of years ago, I actually organized a meeting, a conference, where I brought the biotherapeutic industry together with the food industry. And lots of new collaborations started as a result of that. But it's interesting, once you see the broader picture, you can start to draw inferences from different industries. Okay, yeah. Sorry, lots of questions. No, if you're okay with time, or we can talk offline as well, yeah. Now let's watch the soft water from yeah.
Hi, Zoom. Hi, Zoom participants. Thanks for joining us. Feel free to log out, and the workshop tomorrow starts around 9. We will see you there. Thank you.
Thank you so much. See you tomorrow.